Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight we're going to gently explore the vast, quiet expanse of our universe, not through the hustle and bustle of daily life, but through the patient eyes of humanity's greatest telescopes. These are the silent guardians, the distant listeners, the gentle giants that reach out across unimaginable distances to gather the faintest whispers of light and energy. But don't worry, we'll take it slow. This isn't a race through facts or a lecture filled with equations. It's more like drifting through a galaxy of ideas, wrapped in a blanket of wonder with the soft glow of distant stars as our only guide. We'll listen to the stories that light has carried for eons, stories of colossal structures and elusive particles, all told with a humble reverence for the mysteries that still embrace us. So breathe deeply, let your thoughts unfurl, and allow your mind to wander through the cosmos as we begin our quiet journey. The gentle breeze of knowledge carries us first to a place of quiet power, a true titan among stargazers often referred to as the Very Large Telescope, or VLT. One might understandably find their thoughts drifting towards the future, towards the grand whispers of the extremely large telescope set to grace our skies in the coming years. Yet we must pause and offer a soft nod to its predecessor, the VLT, which continues its silent, relentless work, a testament to enduring vision and quiet productivity. In the hushed halls of scientific discovery, few instruments can truly rival the sheer volume of insights that flow from its gentle gaze. Imagine, if you will, a seasoned storyteller weaving tales of the cosmos. The VLT is that storyteller, its voice steady and clear, producing a new chapter, a new scientific paper more than once every single day. In the year 2019 alone, nearly 600 such stories emerged from its quiet observations, a remarkable number that easily outshines the collective efforts of all other land-based telescopes. Even as the newer, grander instruments begin to awaken with their colossal mirrors, stretching 30 meters and beyond, the VLT will retain its unique place, its special corner in the tapestry of cosmic exploration. It holds a gentle secret, a subtle trick up its sleeve, a whisper of collective power that makes it truly exceptional. This secret lies in its inherent ability to transform. Picture not one solitary eye peering into the darkness, but 8 distinct yet harmoniously connected eyes. These 8 individual telescopes possess the remarkable capacity to unite their vision, to combine their light into what we might imagine as a single, vast, virtual mirror. This combined eye, though not physically present as one continuous surface, boasts an effective diameter of a staggering 200 meters. Think of it as a choir, where each singer is powerful on their own, but when their voices blend, they create a symphony of immense reach and depth, far beyond what any single voice could achieve. This collective strength lends the VLT a punching power, a clarity of sight that far exceeds what one might expect from its individual components. It's a gentle reminder that sometimes unity creates a magic all its own, allowing us to see details that would otherwise remain veiled in the cosmic distance. So, as we settle into this quiet contemplation, we might ask ourselves, what exactly is this very large telescope, this quiet powerhouse, and what profound contributions has its gentle gaze bestowed upon the grand tapestry of science? We are merely humble observers on this journey, seeking to understand how this incredible feat of engineering truly works, and to quietly witness the echoes of its discoveries. Its observations have led us to peer behind the veils of black holes, to feel the distant hum of neutron stars, and even to find subtle confirmations of the grand sweeping theory of general relativity, a testament to the universe's elegant design. The VLT does not shout its achievements. It simply unveils them, one delicate observation at a time, allowing us to absorb their quiet wisdom. The journey of the Very Large Telescope to its current state of operation concluded in a sense in the year 2000. However, that simple sentence, like a softly spoken riddle, carries a gentle misleading quality on two subtle levels. The first, and perhaps most immediate, is hinted at by the very name itself. The Very Large Telescope might suggest a single monolithic mirror, a singular giant eye. Yet, as we have already gently hinted, the VLT is far from a solitary gaze. It is a chorus of light, a gathering of distinct yet interconnected instruments. So is its name misleading, perhaps. But let us quietly consider why, despite its multiple components, it is still embraced as one singular entity, one unified scientific instrument. The initial whispers of its design envisioned a modest array, 4 magnificent telescopes, each rising 25 meters tall, their mirrors stretching a grand 8.2 meters across. These were lovingly termed the unit telescopes, and they were designed with a sense of quiet independence, each capable of studying the distant stars on its own terms. Each one in its solitary pursuit could achieve an angular resolution of 50 milliseconds. To truly grasp the precision of this quiet ability, imagine seeing details smaller than a standard DVD if that DVD were resting gently upon the International Space Station as it glided across our night sky. Such a feat speaks volumes about the meticulous care and engineering that went into crafting each of these individual eyes. The second subtle misleading layer in that seemingly simple statement about its completion in 2000 is that in a profound and ongoing sense, the VLT is never truly finished. It is a living, breathing entity constantly evolving, much like a grand ancient tree that continues to sprout new branches and leaves with each passing season. Even as early as 2004, and then again in 2007, its family grew. A total of 4 new auxiliary telescopes were gently added to the VLT's sprawling array. These newcomers, though smaller with mirrors, a modest 1.8 meters across, brought a new dimension to the collective vision, and the growth did not cease there. Additional instruments, like delicate new senses, have been routinely integrated over the years, some as recently as 2018. There are currently 16 such instruments in quiet operation, ranging from devices that gently separate light into its constituent colors, spectrometers, to those that capture the subtle warmth of the universe, infrared imagers. And the future still holds promises of more additions, whispered possibilities, like, foremost, an upcoming upgrade to the Vista telescope instrument, which itself is an integral part of the sprawling VLT site. This continuous evolution speaks to a deep understanding in the pursuit of cosmic knowledge. Stagnation is not an option. Constant, gentle adaptation is the key. Maintaining such a massive and intricate array of sensitive eyes exposed to the vastness of the open air each night presents a gentle but persistent challenge. The Atacama Desert in northern Chile, where the VLT gracefully rests, is often considered ideally suited for its observations. It is a place of profound stillness so dry that records show no rain has fallen there since measurements began. This incredible aridity ensures skies of unparalleled clarity, a blessing for any stargazer. Yet even in this pristine quietude, nature introduces its own gentle interruptions. Dust, fine and almost imperceptible, can sometimes drift in on the desert winds. This requires a meticulous and delicate ritual. Every 18 months, the colossal mirrors of the VLT must undergo a gentle cleansing. Imagine skilled hands moving with infinite care as chemicals designed to softly remove their existing aluminum coating are applied. And then, with an equally tender touch, a fresh new coating is delicately applied, like restoring the pristine vision of an ancient oracle. This process, despite the grand scale of the mirrors, is surprisingly modest in its material requirements. Only about 12 grams of aluminum are needed to coat an entire 8-meter mirror. To put that into gentle perspective, it's less aluminum than you would find in a single drinks can. This speaks to the incredible thinness of the coating, a mere 80 nanometers thick. Imagine a film so infinitesimally thin, yet so crucial to reflecting the faintest whispers of light from distant galaxies. Each unit telescope, viewed individually, is a pristine feat of human engineering, a monument to precision. These colossal structures, weighing an astonishing 430 tons each, approximately the weight of a jumbo jet, stand as silent sentinels. Yet for all their immense mass, they are balanced with such exquisite perfection on their hydrostatic oil film bearings that a single human hand with a gentle push can set them into motion. It is a dance of colossal weight and feather-light touch, a testament to the elegant simplicity that can be found even in the grandest designs. The mirrors themselves are crafted to such an unparalleled degree of precision that if one were to imagine scaling them up to encompass the entire Earth, any imperfections on their surface would be smaller than a tiny pebble. It is a level of flawlessness that borders on the poetic, allowing them to capture the faintest, most intricate details from the cosmic tapestry. But as impressive as these individual feats of engineering are the truly breathtaking accomplishments, the moments of profound wonder are yet to gently unfold. For all the power and clarity that each unit telescope possesses on its own, it is when they embark on a shared journey, when they work in quiet concert, that they truly transcend their individual capabilities. It is then that they begin to act as one single colossal telescope, their combined vision unveiling secrets that would otherwise remain hidden in the cosmic mists. Let us gently delve into the essence of this remarkable technique, a method known as interferometry, a dance of light waves that allows these separate eyes to see as one. Light in its essence travels in waves. Imagine ripples spreading across a calm pond, each expanding outwards. When you gently combine two such waves, and they align just when their peaks meet in perfect harmony, they do not merely add up, they amplify each other. It is like two melodies weaving together to create a richer, more resonant sound. This simple, elegant principle is the heart of interferometry, a technique that allows the VLT to achieve an astonishing level of detail. Beneath the very ground where the VLT stands hidden from view, there lies a silent labyrinth, a series of underground tunnels meticulously lined with mirrors, arranged in a configuration of exquisite complexity. Into these hidden pathways, the delicate light gathered by the various telescopes is gently fed. The placement of these mirrors within the tunnels is calibrated with an almost unimaginable accuracy down to a tiny fraction of a single wavelength of light. This astonishing precision is crucial, for it ensures that the light from each telescope enters the system in just the right phase, in perfect alignment, so that every tiny ripple of light lines up precisely. In this gentle, yet powerful way, a greater resolution of detail and unparalleled clarity of vision can be achieved. To truly appreciate the VLT's power, let's consider its individual capabilities. A single unit telescope on its own possesses the astonishing ability to peer into the cosmic depths and discern objects that are 4 billion times fainter than what the unaided human eye can perceive. Think of the sheer darkness it can pierce, the subtle glows it can detect from unimaginably distant realms. Yet when the gentle power of interferometry is brought to bear, when these separate eyes unite their vision, this already profound capability becomes 25 times more effective. It is like opening a window to the universe that was previously only a tiny crack, suddenly revealing a panoramic vista of breathtaking clarity. However, it should be gently noted that this amplification of light waves, for all its profound benefits, does carry with it a few subtle drawbacks, a quiet trade-off in the grand design. As light embarks on its intricate journey, bouncing and reflecting through all these precisely placed mirrors within the subterranean tunnels, a portion of that precious light can inevitably be lost. The process, for all its elegance, is not perfectly efficient. Consequently, the celestial object that the VLT is attempting to observe through interferometry needs to possess a certain inherent brightness to begin with. It cannot be utterly faint, for even the most ingenious amplification cannot conjure light where there is almost none. Secondly, and this is a fascinating nuance, interferometry does not by its very nature spontaneously create a full continuous image. Instead, It acts more like a highly discerning filter, picking out merely certain details and distinctive features of what is visible. These captured details often manifest as what astronomers gently refer to as fringes, patterns of light and dark that carry the subtle information. It's akin to hearing a faint melody and being able to discern its underlying harmonies rather than seeing the entire score written out. However, for the discerning purposes of astronomers, this subtle extraction of detail is often quite sufficient. And should a more complete, crisper image be required, the VLT's observational data, these delicate fringes of information, can be meticulously processed through powerful computers. It merely demands a little more time and considerable processing power, transforming these abstract patterns into beautifully rendered cosmic portraits. The VLT's effective 200-meter diameter virtual mirror, crafted by the gentle hand of interferometry, indeed provides exceptional resolution. It allows us to distinguish fine details in distant celestial tapestries that would otherwise remain blurred and indistinguishable. However, it is important to understand that this remarkable resolution does not equate to its ability to collect the same sheer quantity of light as a single continuous mirror of that vast diameter, such as the future 30-meter mirror. There is quite obviously a great deal of empty space that remains between the individual unit telescopes. These vast stretches are not covered by mirrors, and thus they are not actively collecting any light. It is a distinction between the ability to see sharply and the ability to gather every single photon. Yet what the VLT does perceive, what it does reveal through its gentle but powerful vision, is nothing short of revolutionary. Its discoveries span the spectrum from the purely beautiful, such as its eye-catching ethereal glimpse of the spiral galaxy NGC 1398, a cosmic bloom painted in swirling starlight, to the utterly groundbreaking. Among these profound unveilings is the first ever image taken of an exoplanet, a distant world orbiting another star, a faint, solitary beacon of light in the vast cosmic ocean. The VLT is often found at the very forefront of discovery, its quiet observations leading the way into uncharted territories of cosmic understanding, exoplanets. These elusive worlds beyond our solar system are typically detected through far more indirect means. Often their presence is inferred by the subtle absorption of light as it filters through their atmospheres like a delicate veil, or by the almost imperceptible dimming of any stars they happen to pass in front of a tiny flicker in a distant lamp. It is exceptionally rare, a truly cherished moment, to obtain an actual tangible photograph of one of these distant worlds. And yet, in the quiet year of 2004, the VLT achieved this remarkable feat, capturing an image of a world known as 2M7b. This was a Jupiter-like planet, a giant gas world resting gently in the Hydra constellation, a staggering 230 light-years away from our own home. This incredible image was captured with the quiet aid of a system known as NACO, the Nasmyth Adaptive Optics System. This system has since been gently replaced by even more advanced optical marvels, now collectively known as Naomi, the new adaptive optics module for interferometry. According to the ESO website, these new modules are, in their own gentle words, putting the VLT's interferometer on steroids, hinting at an even greater sharpening of its already keen vision. It is worth noting, in our quiet journey through these technological wonders, that adaptive optics is an absolutely vital component of any ground-based telescope seeking profound clarity. Imagine the atmosphere above us, a restless, shimmering ocean of air. As light from distant stars carrying its ancient stories journeys millions of miles to reach our telescopes on Earth, it must first contend with this ever-moving, ever-changing veil. The movement within the atmosphere causes subtle distortions in the incoming light, much like looking at the bottom of a swimming pool on a sunny day. This distortion can blur the intricate details, making it much harder for us to truly make out the delicate features of distant celestial objects. This, in essence, is the primary advantage that space-based telescopes hold over their ground-based counterparts. In the vacuum of space, there is no atmospheric ocean to contend with between the observer and the observed object. The view is pristine, unblemished. However, the VLT's adaptive optics system showcases an ingenious, elegant solution to this persistent challenge. It is a quiet dance with the atmosphere, a continuous act of compensation. The VLT achieves this by utilizing either nearby guide stars, stars whose light is known and predictable, or if no suitable natural guide star can be found, by creating its own artificial stars using powerful lasers projected high into the atmosphere. The VLT then meticulously tracks the distortion taking place as a direct result of the atmosphere's subtle movements. It does this by observing how the light from these guide sources deviates from what it should ideally be, sensing the atmospheric wobble. Then, with an astonishing swiftness, using tiny delicate actuators positioned beneath the very mirrors of the unit telescopes themselves, the VLT introduces minute, real-time distortions in the mirror's surface. These subtle, precisely calculated changes act as a direct countermeasure to the distortion in the air. This continuous quiet ballet of correction can effectively negate much of the negative effects of the atmosphere, granting the VLT a significantly clearer, much better look at the intricate tapestry of the universe, allowing its gentle gaze to penetrate deeper and more sharply than would otherwise be possible from our terrestrial perch. So having gently explored the intricate workings of the VLT, let us now softly drift into some of its most profound discoveries, the quiet whispers it has brought back from the cosmic ocean. With such an abundance of data, such a rich tapestry of information to choose from, it truly becomes a matter of picking out a few personal favorites, like selecting the most luminous pearls from a vast, shimmering collection. The VLT has turned its patient gaze towards the dramatic aftermath of colliding neutron stars, those incredibly dense remnants of stellar collapse. In a groundbreaking first, it detected the faint spectral signature of freshly made heavy strontium, an element that, rather ironically, lends its vibrant color to the fireworks we enjoy on Earth. Imagine then the VLT's quiet detection of this element, born from a cosmic cataclysm, now glowing gently in our celebratory displays. It has also, with quiet precision, measured the temperature of the distant universe. By delicately detecting carbon monoxide atoms, ancient messengers from afar, the VLT confirmed a profound truth that 11 billion years ago, the vast expanse of space was indeed slightly warmer than it is now. A subtle difference, perhaps, but a significant one to the delicate understanding of cosmic evolution, minus 264 degrees Celsius, then, versus a chilling minus 270 degrees Celsius today. So admittedly still quite chilly, but a gentle confirmation of the universe's slow, steady cooling. But perhaps among all the exciting revelations the VLT has brought forth, its most profound and quietly thrilling role was its contribution to helping prove the grand theory of general relativity. This achievement, a testament to decades of patient observation and brilliant minds, ultimately earned Professor Reinhard Genzel the Nobel Prize for Physics in 2020. This was not merely about confirming an abstract theory. It also involved the quiet, undeniable confirmation of the existence of a truly monstrous black hole lurking silently at the very center of our own Milky Way galaxy. Einstein's magnificent theory of relativity had for a long time quietly predicted the existence of black holes. As far back as 1916, Carl Schwarzschild had gently shown that these enigmatic objects were a natural consequence of Einstein's equations. For decades thereafter, scientists pondered with a mix of wonder and skepticism whether these universe-warping entities truly existed, or if they were merely beautiful mathematical constructs, figments of theoretical elegance. Then, in 1965, a brilliant mathematical physicist named Roger Penrose embarked on a profound intellectual journey. In his seminal paper, Gravitational Collapse and Space-Time Singularities, he went on to prove with quiet certainty that black holes were not just abstract mathematical artifacts within Einstein's theory, but concrete, inevitable certainties. He showed that it was inescapable. They could and indeed would form under the right cosmic conditions. Yet despite these powerful theoretical confirmations, it still took until the turn of the millennium into the quiet dawn of a new era before the first black hole was truly observationally confirmed. During this period of patient anticipation, scientists began to softly suspect that one such colossal black hole resided at the very heart of our own galaxy. Whispers of its presence had been circulating for decades, dating back to 1931, when faint radio signals were first detected emanating from the galactic center, a region nestled some 25,640 light-years away in the constellation of Sagittarius. In 1971, two radio astronomers, Bruce Balick and Robert Brown, with a keen sense of observation, noticed a bright compact object at our galaxy's core that was eventually given the humble name Sagittarius AES. But for many years, the telescopes of the time, for all their growing power, were simply not sensitive enough, not sharp enough to truly peer into the turbulent heart of Sagittarius A and confirm its true nature. This quiet impasse began to shift with the dedicated work of two remarkable astronomers, Andrea Ghez and Reinhard Genzel. In the 1990s, they embarked on a monumental undertaking, a project that would span nearly 3 decades of meticulous observation. Each astronomer, working with their respective teams, began to patiently map out the intricate motion of individual stars in the crowded center of Sagittarius. Their goal was to gently observe how these stars interacted with the unseen gravitational presence of Sagittarius AEX. General relativity, with its profound predictions, foretold a rapid, almost dizzying movement for any star daring to pass close to a black hole. However, it also predicted a more subtle, yet equally profound phenomenon, precession. This was a gentle, gradual change in the orbital path of the star over time, subtly shifting in the direction of the star's motion, rather than simply tracing a perfect circle or an elegant ellipse. A star exhibiting such precession would follow the graceful, intricate path of a rosette through the vastness of space. But to confirm this subtle dance, this cosmic rosette required incredibly detailed evaluation of the stars circling Sagittarius A for multiple orbits, and each orbit for these distant, slow-moving cosmic dancers could last up to 16 years, so decades of patient observation, a quiet vigil under the stars, were absolutely necessary to gently confirm Einstein's profound theory. Fortunately, by this crucial juncture, powerful telescopes like the VLT had become available, ready to lend their sharp eyes to this long-standing mystery. Genzel's dedicated team made extensive use of the VLT, turning its gentle gaze towards the subtle motions of the stars around Sagittarius A. Simultaneously, Andrea Ghez, with equal dedication, utilized the Keck Observatory in Hawaii to conduct parallel observations. Together, these two brilliant teams, by combining their meticulous data and their quiet perseverance, were able to confirm that this gentle precession was indeed taking place. As further compelling evidence, in 2018, the VLT observed the star S2, a cosmic ballet dancer, gracefully tracing its path around Sagittarius A at an astonishing speed, 7,650 kilometers per second, or 2.55% the speed of light. This velocity was precisely in line with the speeds that Einstein's theory had so elegantly predicted. This final quiet confirmation solidified Sagittarius A's identity as a supermassive black hole, an immense compact object anchoring the very heart of our galaxy. Thus, in the quiet year of 2020, both Andrea Ghez and Reinhard Genzel received the Nobel Prize in Physics for their profound discovery of a supermassive compact object at the center of our galaxy. And in a beautiful recognition of foundational insight, Roger Penrose, who had first mathematically proven that black holes inevitably arose from Einstein's theories, also received a share of the Nobel Prize for his quiet foundational work. So there you have it, the VLT, a quiet force has been profoundly influential up until this very moment, providing a steady stream of invaluable data that has enriched countless scientific papers. It has, through its consistent, meticulous work, firmly established itself as one of the most productive telescopes humankind has ever conceived. Yet, as we gently turn our gaze towards the future, an era where extremely large telescopes are beginning to emerge as common features on the cosmic landscape, and as magnificent instruments like the James Webb Space Telescope gracefully orbit our skies, the VLT will, like all venerable institutions, need to continue to adapt, to maintain its relevance. To truly stay current in this accelerating journey of discovery, it will need to subtly up its game. This evolution will manifest in a continuous gentle refinement. Its instruments will need to be regularly updated and modified, like tuning a beloved old instrument to sing new melodies. The VLT, with its inherent versatility and profound capabilities, still holds immense potential for many more years of valuable contribution to the scientific community. The astronomers, those quiet architects of understanding, will need to think carefully and strategically about how best to achieve this continued excellence, how to ensure its gentle gaze remains sharp and insightful. But in truth, it should not be an insurmountable challenge. The VLT is at its heart a powerhouse, a testament to enduring design and adaptability. We can be certain it will continue to find its unique niche, its special place in the cosmic symphony for many years to come, quietly unveiling new wonders with each passing night. Now let us gracefully transition our attention to another marvel one that has been capturing headlines and hearts with its golden promise, the James Webb Space Telescope, JWST. This magnificent spacecraft, named after the visionary NASA administrator who oversaw the Apollo moon landings, is not merely a telescope. It is a veritable cosmic behemoth, the largest, most powerful, and most intricately complex space telescope ever brought into being. It has been hailed quite rightly as the successor to the venerable Hubble, which itself for decades played an instrumental role in gently expanding the boundaries of our understanding of the universe. The journey of the JWST has been one of immense dedication and perseverance. It has undergone major redesigns since creation, incurring a substantial cost of $9.7 billion, and its development, construction, and rigorous testing spanned an astonishing 25 years. There were moments during its decades-long genesis when its very existence hung in the balance, when it was perilously close to being canceled entirely. And yet, with the quiet aid of scientists and engineers from several nations across the globe, it has, with a quiet resilience, overcome hurdle after formidable hurdle. But for all this immense investment of time, money, and human ingenuity, this incredible instrument, once gently unfurled in the cold vacuum of space, will only last for a maximum of 10 years. This fact prompts a profound question, a gentle whisper in the mind. Why have scientists undertaken the construction of such a colossal telescope? Why pour all this time, all this precious money, and all this tireless effort into building something that, relatively speaking, will be so short-lived in the grand cosmic timeline? The answer, profound and elegant, lies in its unparalleled ability to peer through time itself. The JWST, in a way unlike any instrument before, it will allow us to glimpse the very beginnings of the universe, to witness the quiet dawn of creation. Join us now as we gently explore how this incredible spacecraft, a triumph of human ingenuity, will allow scientists to pull back the curtain on the formation of the very first galaxies, those primordial islands of stars that came into existence after the grand silent symphony of the Big Bang. Together, we will uncover the intricate science and meticulous engineering that went into its making, as well as the formidable challenges it gently faced. For this truly is a spacecraft that promises to unlock clues to the universe's origins like no other, a golden key to an ancient cosmic puzzle. The story of the James Webb Space Telescope softly began in 1996. At that time, NASA had been quietly contemplating for several years the concept of a next-generation space telescope, NGST. Their aim was to gather elusive data to unlock deeper secrets of the cosmos. The initial whispers of this ambitious plan envisioned an 8-meter aperture telescope, a formidable eye with an estimated cost of approximately $500 million. However, as the quiet march of time progressed, decision-makers began to realize with a growing sense of awe that far more resources, far greater dedication of human ingenuity, and financial investment would be needed to truly achieve their profound aims. But what precisely were these aims? What cosmic secrets did they yearn to unveil? The NGST, the nascent seed of the JWST, was conceived to be primarily an infrared telescope. The venerable Hubble, a true pioneer, had been quietly functioning since 1990. Its primary range centered on the visible light and ultraviolet spectrums. While Hubble did possess some limited infrared detection capability, its true strength lay elsewhere. This distinction raises a gentle yet crucial question. Why did scientists so earnestly desire a powerful infrared telescope? The answer, like a fundamental truth whispered from the heart of the cosmos, comes down to some deep and inherent facts about the universe itself. Scientists believe that our universe, as we perceive and understand it, has existed for approximately 13.8 billion years. The question of its genesis, how it all began, remains a profoundly fascinating inquiry, one that has inspired countless theories and quiet contemplation. Current mainstream theories gracefully revolve around the majestic idea of a Big Bang. Imagine, if you will, a time when all matter, all energy existed in a space so infinitesimally small that it was effectively zero. Atoms in their familiar forms did not even exist at that primordial stage. They would have been far too large, too complex for that compressed reality. Then suddenly, with a quiet, immense expansion, everything burst outwards at once, not an explosion in space, but an expansion of space itself. Matter began to gently coalesce, first into the most basic atoms, then into the delicate wisps of cosmic dust, which in turn gathered into the fiery hearts of stars and the nascent forms of planets. And ever since that momentous beginning, the universe has been steadily, gently expanding and cooling, like a vast, breathable exhalation. But wouldn't it be profoundly helpful, a source of immeasurable insight, to be able to look back to truly see for ourselves those first moments of creation? Or to witness the majestic formation of those very first galaxies? Such a direct glimpse, a silent observation of cosmic infancy, might offer us unparalleled insights into the precise mechanisms of how all of it, this grand, intricate reality we inhabit, truly came into being. The James Webb Space Telescope, with its golden infrared eye, holds the promise of either providing powerful evidence to gently reinforce the Big Bang theory, or in a truly revolutionary turn, completely transforming our current understandings, reshaping the very fabric of our cosmological theories. This profound capability is thanks to a fundamental truth about light itself, at least to a certain gentle point. While light is blindingly fast, a true cosmic sprinter, its journey is not instantaneous. There exists a tiny, almost imperceptible time delay between when light is first emitted from its source and when our eyes or our sensitive instruments finally perceive it. Photons, these elusive particles of light, travel at an unwavering constant rate, precisely 299,792,458 meters per second in a vacuum. To grasp this concept more intimately, consider our own sun nestled some 148 million kilometers from us. This means that it takes approximately 500 seconds for sunlight to embark on its journey and finally reach our planet. So what you quietly perceive when you gaze at the sun in the sky right now is not the sun as it is in this precise moment, but rather the sun as it was a mere 8 minutes and 20 seconds ago. It is a gentle glimpse into its very recent past. This time delay becomes increasingly profound, stretching into vast cosmic scales. even when we consider objects that are relatively speaking quite close to us. Proxima Centauri. Our next nearest stellar neighbor is so immensely distant from Earth that its light journeying across the interstellar void requires a full 4 years to finally arrive at our planet. All of this quiet understanding leads to a breathtaking conclusion for objects that are progressively further and further away from us. We are seeing them as they existed further and further back in time. If by some cosmic alignment there existed an object sufficiently far away, we would be privileged to observe it as it was 13.8 billion years ago, precisely near the very origin of our universe. And fortunately, as many gentle theories speculate, we exist within an infinitely vast universe, meaning that such unimaginably distant objects should in fact exist. With the James Webb Space Telescope, we hold the quiet hope of finally being able to see them, to witness the echoes of the universe's infancy. But why, we might gently ask again, does the James Webb Space Telescope specifically view the universe in the infrared spectrum? One compelling reason, a practical advantage, is that infrared light possesses a unique ability. It tends to punch through clouds of cosmic matter with greater ease. Imagine trying to see through a dense fog with your naked eye. Now picture a special light that can softly penetrate that fog, allowing you to glimpse what lies on the other side. This property allows the JWST to peer past otherwise opaque gas clouds and dusty veils, revealing the hidden celestial wonders that lie beyond. However, the main and most profound reason, the one directly relevant to our quest to glimpse those elusive early galaxies, stems from a second beautiful quirk of the universe: the undeniable fact that space itself is expanding, for reasons that remain a profound mystery. Reasons that scientists currently theorize are the subtle work of dark energy. Everything in the universe is gently yet relentlessly moving away from everything else in a continuous quiet ballet of separation. As a distant star or galaxy gracefully recedes from us, the light emanating from it is stretched, elongated in a process known as the Doppler effect. And because the wavelength of light is the very characteristic that defines the color we perceive as light stretches, it gradually shifts further and further towards the red end of the spectrum. This phenomenon is commonly referred to as redshift, but this cosmic expansion is not uniform or constant. Scientists have observed with quiet precision that the further something is away from us, the faster it is expanding away from us. This gentle acceleration of expansion means that light from the very furthest galaxies, those ancient beacons from the dawn of time, has been stretched so profoundly, shifted so far into the red, that it has actually gone beyond the visible red, drifting into the imperceptible frequencies of infrared light. The venerable Hubble, for all its groundbreaking achievements, was simply not fully designed to detect these extended infrared frequencies with the sensitivity required. The James Webb Space Telescope, however, has been meticulously crafted precisely for this purpose. Its sensitive receptors are capable of detecting light at frequencies ranging from 0.6 micrometers to a grand 28.5 micrometers long. Interestingly, this specialized focus means that the JWST actually cannot perceive all visible light frequencies. It possesses the ability to gently discern red and a substantial portion of orange frequencies, but nothing beyond yellow. Its primary focus, its quiet strength, lies firmly within the infrared frequencies. In this gentle way to simply state that the James Webb Space Telescope is a direct replacement for Hubble is, in a factual sense, incorrect. NASA, with its nuanced understanding, prefers to describe the James Webb as an instrument that supports and complements Hubble. Each telescope, with its unique vision, will focus on frequencies of light that the other does not perceive with the same clarity. Besides considering that Hubble could potentially continue its quiet observations until 2040, it is quite likely that it will actually outlast the James Webb Space Telescope, making James Webb an intriguing, if temporary, replacement. Still, the profound capability to perceive these delicate infrared rays from such unimaginably distant sources represents a truly immense quiet challenge. Imagine holding a flickering candle on a clear dark night with a friend holding another. As you gently walk away from each other, it wouldn't be long before your candle began to appear dimmer, its light fading into the vastness. This quiet fading is due to a fundamental principle known as the inverse square law, where light photons gently spread out as they travel, diminishing in intensity with distance. Furthermore, light has a subtle tendency to scatter when it passes through matter, even the thinly dispersed particles of dust in the seemingly empty void of space. And although space is indeed extremely empty, a vast and quiet vacuum, there are still enough tiny particles of dust gently floating around that over the immense distances of cosmic travel objects that are truly far away become progressively more difficult to see, their light scattering like soft whispers lost in the wind. To gently combat this pervasive fading, the James Webb Space Telescope houses a magnificent gold-plated beryllium mirror that spans a colossal 6.5 meters in diameter. This makes its light-gathering surface area an astonishing 6 times larger than that of Hubble's mirror. This larger mirror is meticulously designed to gently catch more of the fleeting light from distant sources, like a colossal patient net, before meticulously focusing it back into the telescope's sensitive instruments. This allows them to pick up the very faintest traces of radiation, the most delicate echoes from the early universe. Furthermore, as its very name suggests, the James Webb Space Telescope is a space mirror. Its profound advantage lies in its celestial perch far above the Earth's restless atmosphere. Being in space means that the telescope does not have to contend with the Earth's atmospheric veil, that ever-moving ocean of air that can subtly refract and distort light waves as they pass through it. The pristine vacuum of space provides an incomparably clearer view, a quiet, unblemished window allowing James Webb to effortlessly find those tiny diffuse infrared waves, those ancient stretched whispers of light, with much greater ease and fidelity. The journey of James Webb does not end with its launch. It will be gently guided to orbit the Earth in a very specific celestial address, a position known as the L2 Lagrange point. This unique location in space, while not technically a true orbit in the traditional sense, rests approximately 1.5 million kilometers from the Earth, nestled at the point furthest away from the Sun relative to Earth's position. For a gentle point of reference, consider our Moon, which silently orbits at a mere 384 or 400 kilometers from Earth. So the JWST's destination is vastly further out, a truly remote and solitary vigil. Due to the intricate way the Earth's gravity gently interacts with the Sun's, this particular point in space is gravitationally stable, a kind of cosmic eddy. This stability makes it far easier for an object to gracefully hover there with minimal effort, requiring only gentle nudges to maintain its position. This profound stability makes it an ideal viewing station for an orbital telescope, a place of quiet contemplation. One spacecraft has already quietly visited this serene spot, the Planck Space Observatory, a pioneer in its own right. The immense distance from Earth, while challenging for human visits, offers a crucial advantage. The James Webb Space Telescope does not have to contend with any stray radiation gently bouncing off the Earth or the Moon, which could otherwise interfere with its sensitive observations. Yet it remains close enough that it can reliably send its precious signals back to Earth, quietly whispering the wonders it perceives. Naturally, at such a remote and isolated position, it will be exceedingly difficult, almost impossible, for us to physically visit the James Webb Space Telescope. So even though James Webb was thoughtfully designed with a docking ring, a subtle hint of future possibilities, the current plan is for there to be no missions to physically service or replace its parts once it has settled into its celestial home. Once it is gently unfurled and positioned, its fate, for the most part, rests in the quiet, precise dance of its own mechanisms. While it needs minimal effort to maintain its delicate position, minimal is not zero. James Webb carries enough precious fuel to maintain its station for at least 5 years, and at most 10. After that silent deadline, it will, with a quiet resignation, begin to decay from its orbit and will no longer be able to function as intended. It carries in its very design a guaranteed expiration date, a gentle reminder of the finite nature of even our grandest endeavors. One final beautiful benefit of this remote celestial position, the L2 Lagrange point, concerns temperature. Heat in its very essence travels in infrared waves. The heat gently generated by the telescope's own internal parts could, if left unchecked, potentially blind its incredibly sensitive infrared sensors like a bright light shining directly into a camera lens. However, thanks to its unique and solitary position in space, James Webb will be able to cool itself to astonishingly frigid temperatures, plummeting to minus 223 degrees Celsius. This profound cooling is also greatly aided by its remarkable solar shield. You have no doubt noticed the vast silvery canvas stretching out from the bottom of the satellite like a colossal protective fan. This 5-layered shield, astonishingly, the size of a tennis court, is meticulously designed to point continuously in the direction of the sun, earth, and moon, gently blocking the relentless heat emanating from them, ensuring the telescope remains in its deep operational chill. With that last fact, you may have begun to gently realize the sheer scale of this satellite, the James Webb Space Telescope. It is truly vast, a cosmic leviathan, roughly 20 meters by 14 meters in dimension, and weighing almost 6,500 kilograms. This immense size immediately raises a fascinating, perhaps even perplexing question. How indeed are they going to gently guide this colossal telescope into orbit? The answer, like a whisper of human ingenuity, is explained by one of the most frankly astounding engineering aspects of this telescope: its profound capacity to fold up and then, with an elegant, deliberate grace, unfold itself once it reaches its celestial destination, the Ariane 5 rocket. The powerful vehicle that will cradle and carry James Webb into the dark embrace of orbit possesses a fairing with a 5-meter diameter. This dimension is simply not sufficient to comfortably fit the immense bulk of the James Webb Space Telescope in its fully extended form. As such, James Webb has been meticulously designed so that its primary mirror can fold inward like the petals of a delicate flower at dusk, and its vast solar shield can similarly unspool and reduce its total dimensions, while it rests within the rocket's protective embrace. Once it has been launched, and as it gracefully traverses the silent expanse of space on its solitary journey to the L2 Lagrange point, the James Webb Space Telescope will begin its gradual unfurling, a delicate choreographed ballet of precision. Arms will gently unfurl, shields will slowly unspool, and the hexagonal segments of the primary mirror will meticulously rotate into their precise positions. Then, with the aid of tiny, almost imperceptible motors, these segments will align themselves with a breathtaking precision, ensuring they are perfectly flush with each other. All of this intricate unfolding is meticulously orchestrated to allow it to go about its incredibly delicate business of gathering the faintest whispers of radiation from the dimmest lights in the sky. Mastering this profoundly complex process, ensuring such a sensitive and intricate device can reach orbit and deploy without a single component breaking, is the very reason James Webb has taken such an astonishingly long time to build. It is a testament to human patience and meticulousness. Remember, once launched, once it begins its solitary journey, there is no chance of sending a repair crew, no possibility of going up there to gently fix it if something were to break during the deployment sequence. If even a tiny flaw were to occur during this critical unfolding, it could well spell the quiet end of the entire mission, wasting over 2 decades of tireless work and an astounding $9.7 billion. In 2005, just a few short years before its initially intended launch date, the entire project underwent a fundamental redesign, a quiet re-evaluation of its very core. Every single aspect was checked and double-checked by meticulous review boards, a painstaking process of ensuring every thread of the tapestry was perfectly woven. In 2018, the project faced a further disheartening delay when a test of deploying the vast solar shield resulted in it ripping. A thorough review of what went wrong, a quiet post-mortem uncovered an additional 344 potential single-point failures, any one of which, if it were to break, would mean that the entire complex mechanism would simply cease to work as intended. When the costs, like an unstoppable tide, began rising significantly in 2011, the American Congress made a move to reduce NASA's budget, a quiet step towards potentially canceling James Webb altogether. However, the ensuing public backlash, a collective wave of support for the project, ultimately led them to reverse their decision, allowing the Golden Dream to continue its slow, determined progress. The James Webb Space Telescope, a beacon of international collaboration, was meticulously built by NASA in quiet cooperation with the European Space Agency and the Canadian Space Agency. It has faced delays over 13 times its project costs, as we've noted, swelling from a humble $500 million to an astounding $9.7 billion. But finally, very soon, it will be here. Its profound mission, to gently peer into the very heart of space and quietly uncover the mysteries of the formation of the first galaxies, stars, and planets, will finally begin. You can be certain that when it gracefully launches from the European spaceport in French Guiana, there will be countless individuals around the globe waiting with hushed anticipation for news of a successful launch. And you can also be certain that once it is suspended in the vastness of the sky, scientists will be contending with quiet determination to get a chance to look through its golden eye, to be among the first to gently discover what wonders it reveals. So, we offer our quiet good luck for the launch and the deployment to all the dedicated teams involved with this monumental endeavor. If it works, this instrument will undoubtedly be the most significant development for space science for potentially decades to come. We are all, in this humble observer's opinion, rightfully excited about the James Webb Space Telescope. Such a powerful space telescope, once fully operational, will allow us to see things extremely far away with a heretofore unprecedented fidelity, a clarity that promises to reshape our understanding of the universe. However, as we gently conclude our thoughts on the JWST, another remarkable telescope also due to be completed in the same quiet year of 2021 has received far less public attention. It is a ground-based project that, despite its top ranking in the Astrophysics Decadal Survey of 2010, remains largely unspoken of by the wider world. What is it, we might softly ask, and what quiet purpose does it serve? Why do astronomers, those dedicated seekers of cosmic truth, consider this project to be quite so profoundly important? Join us as we gently journey through everything one could wish to know about the Vera C. Rubin Observatory, a true marvel in its own right, yet one that often prefers to work in the background, a silent, tireless sentinel. Very interestingly, the Rubin Observatory is not directly connected to a major space agency, a departure from the grand state-funded projects we often hear about. Its funding has instead gently flowed from the United States National Science Foundation and the Department of Energy, a testament to a broader collaborative vision of scientific discovery. And its careful management is overseen by the Association of Universities for Research in Astronomy, a collective of academic minds dedicated to advancing our cosmic understanding. It is also by a beautiful coincidence of nature being built in Chile, a land already home to many of ESO's esteemed telescopes. But these are not directly connected. Chile simply happens to be an almost magically ideal place for a ground-based telescope, with its towering mountain ranges offering natural elevation and little to no cloud cover, ensuring skies of profound clarity. This geographic blessing is not merely coincidental. It is profoundly important because the Rubin Observatory's primary overarching goal is to survey the entire visible sky every few days. Imagine a tireless eye gently sweeping across the heavens, capturing every visible star and galaxy, a continuous living map of our cosmic neighborhood. It will achieve this monumental task with its incredible 8.4-meter mirror and a staggering 3.2 gigapixel camera. To truly give you a gentle sense of the scale involved, consider this: the mirror itself is the width of a tennis court, a vast reflective surface, and the camera, a marvel of modern engineering, is the largest ever constructed, a silent digital eye, 3 meters long and about 1.6 meters wide. The impressive length of the camera allows the telescope to view an astonishing 3.5 degrees of the sky simultaneously. This is a truly vast area of the sky. For comparison, both our moon and the sun appear to be only about half a degree across from our perspective. This remarkable camera is also capable of viewing a wide spectrum of light, from the near ultraviolet to the near infrared wavelengths. It achieves this versatility with the aid of a robotic arm that gently changes filters, like switching between different colored lenses placed in front of its sensitive sensors. You see certain celestial objects or events that quietly unfold in our sky, shine brighter, reveal more of their subtle secrets in specific wavelengths of light. But what precisely is the Rubin Observatory designed to look at? What cosmic narratives will it gently unveil? Because it is conducting a comprehensive sky survey, its gaze is incredibly broad, seeking out pretty much everything that twinkles or drifts in the night sky. Its particular scientific goals, those specific mysteries it hopes to unravel, are manifold and profound. It aims to search for subtle evidence of dark matter and dark energy, those enigmatic components that shape the very fabric of our universe, yet remain unseen. It will meticulously map small objects within our solar system, particularly those near-Earth asteroids that might pose a gentle cosmic risk, as well as larger, more distant objects residing in the Kuiper Belt. It will patiently detect supernova, those brilliant, fleeting stellar explosions, both within our own galaxy and far beyond. It will track gamma-ray bursts, short, intense flashes of high-energy light, and monitor the variability of quasars, those incredibly bright, distant galactic nuclei. It will seek out gravitational lensing, the gentle bending of light by massive objects, and lastly, but no less importantly, it will meticulously map the countless stars that reside within our own Milky Way, creating a detailed census of our cosmic home. There have of course been plenty of sky surveys in the quiet annals of astronomy, each contributing its own precious insights. Notable mentions include the impressive works carried out with Gaia Pan-STARRS DESI and the Sloan Digital Surveys. These projects have proved immensely useful, meticulously mapping our cosmic surroundings with extreme accuracy, cataloging galaxies, stars, and asteroids with quiet dedication. However, the Rubin Observatory, with its unparalleled breadth and depth of vision, promises to see so much more than any of these previous surveys. At the end of its projected 10 years of tireless operation, it is expected that the vast sea of data flowing from the Rubin Observatory will allow us to catalog 10 to 100 times more asteroids larger than 140 meters than what we currently know about. This represents approximately 62% of what likely exists in a near-Earth orbit, a truly profound increase in our understanding of the potentially hazardous celestial bodies that share our cosmic neighborhood. With its incredibly wide field of view, the Rubin Observatory holds another fascinating promise. Gravitational wave events, those gentle ripples in space-time detected by instruments like LIGO, might become visibly apparent in images captured by the Rubin Observatory. LIGO 2 is predominantly a National Science Foundation project, a very special type of observatory that uses massive mirrors placed 4 kilometers apart, capable of detecting a change less than 1,000th the charge diameter of a proton. These infinitesimal changes can occur as gravitational waves. Those quiet echoes of cosmic cataclysms gently pass through the facility. The sources of these waves typically originate from truly colossal events like the silent, violent collision of neutron stars or black holes. which creates a ripple in spacetime that propagates outwards from the location of the event like a stone dropped into the cosmic pond. These events are usually so immensely far away that by the time their gentle ripples reach us, we require a truly sensitive observatory like LIGO to even discern their presence. Gravitational waves, those ethereal messengers, travel at the speed of light. So if we detect these profound ripples, there should also in principle be light emanating from the very same source. With such events, due to the subtle way we detect them with LIGO, we only roughly know the general direction from which they might have originated. To visually confirm them with a traditional telescope, precious time is often spent scanning vast swathes of the sky, by which point the fleeting optical signal may well have been missed. However, imagine a telescope like the Rubin, capable of seeing a truly significant chunk of the sky at the very same time equipped with a super high-resolution camera. Such an instrument can take a vast number of photos, and later, the captured data can be meticulously searched, sifted through with quiet patience to try and locate the precise event and see if its optical counterpart was indeed visible. It is a game of cosmic hide-and-seek where the Rubin Observatory becomes the tireless seeker. So how will the Vera C. Rubin Observatory, this gentle, persistent eye, manage to achieve these ambitious scientific goals? The telescope, in its tireless work, will typically observe a particular section of the sky for a brief, precise 15 seconds. This 15-second exposure is a carefully considered compromise, a delicate balance between two crucial needs: the ability to discern incredibly faint objects, like the ghostly glow of distant stars that whisper across eons, and the capacity to track swiftly moving objects, such as the numerous asteroids that gracefully, or sometimes not so gracefully, traverse our solar system. If the exposure were significantly longer, while it might indeed capture even fainter objects, the images would inevitably be marred by streaks from these moving celestial bodies, like blurred brush strokes on a delicate painting, thus ruining the shots for their intended purpose. To gently eliminate the subtle noise that can arise from cosmic rays, those energetic particles from space striking the camera sensor, two images of the same region will always be taken in quick succession. These twin images can then be gently merged, revealing the true clearer picture beneath the fleeting imperfections. The sheer scale of the camera's images will be immense, so vast that a single year's worth of data captured by this tireless eye will amount to approximately 1.28 petabytes. To offer a gentle perspective, that's equivalent to about 1,280 terabytes of information, a truly colossal digital library of the cosmos. And because the observatory itself is nestled high in the mountains of Chile, while the primary data processing facility is located thousands of miles away in the United States, a very special dedicated internet connection, a silent digital umbilical cord, had to be specially constructed between the two locations. This robust link, designed to handle a breathtaking 100 gigabits per second, ensures the seamless, gentle flow of cosmic data across continents, bringing the universe's whispers to our analytical minds. Unfortunately, however, there is a rather significant challenge, a subtle problem that has quietly emerged, one that the designers may not have fully envisioned when they were in the meticulous planning and early construction phases of this profound project. Can you guess with a gentle contemplation what might now subtly affect a highly sensitive ground-based telescope, something that wasn't such a pervasive issue even just 10 years ago? It's not the familiar culprits, like atmospheric pollution or the light spilling from our bustling cities. No, it is surprisingly the tens of thousands of CubeSats currently being launched into space by commercial entities like SpaceX and Amazon. Imagine, if you will, a delicate photographic plate capturing the faint glow of a distant nebula. If a tiny, yet comparatively bright satellite happens to pass through the telescope's field of view, during an exposure, it will, like a fleeting bright scratch across the lens, inevitably ruin the shot. This is because these satellites, even small ones, are incredibly bright, when contrasted with the exceedingly dimmest objects that the telescope is tirelessly seeking to observe. As a gentle response to this growing concern, SpaceX has made a quiet commitment to painting their future satellites black or sending them up with a kind of sunshade designed to subtly reduce their brightness. However, it must be acknowledged that this will certainly not completely negate the problem. In reality, the low Earth orbit, that increasingly crowded orbital highway, is only going to become busier and busier, a bustling thoroughfare for humanity's ever-growing presence in space. This quietly puts a serious dampener on the future prospects of highly sensitive ground-based telescopes, a subtle shadow cast over their potential. The truly serious issue here, a matter for broader reflection, is that there are currently no internationally agreed-upon regulations about what can be placed into low Earth orbit. It is, in a sense, still the Wild West out there, a frontier without clear boundaries or rules. And this is not even to mention how this increasing congestion subtly increases the chances of Kessler syndrome, a theoretical scenario where collisions in orbit create a cascade of further debris, making space unusable. But that is a story for another quiet contemplation. All in all, despite these emerging obstacles, this remains a very exciting project. And even with these gentle challenges, we are certain it will acquire a wealth of valuable data, a treasury of cosmic insights. Perhaps in its tireless sweeps, it will even witness events we have never even conceived possible before quietly unveiling new mysteries. So there you have it, a gentle insight into one of the most exciting, yet perhaps lesser-known telescopes, one that we hope more people will begin talking about. While the James Webb Space Telescope continues to capture headlines and imaginations as the most exciting future space project, there is another ground-based telescope currently under construction that hasn't garnered as much attention. And yet, when completed, it will, in terms of sheer scale and light-gathering power, make even the magnificent James Webb Space Telescope look like a minnow in comparison. We are with quiet anticipation introducing ESO's Extremely Large Telescope, or the ELT. So what is it, we might softly ask, and what profound achievements does it hope to attain, and how in its grand designs does it compare to the many other ambitious telescope missions already out there? Join us now as we gently explore the ELT and quietly ponder why it may truly be the most exciting telescope project of the decade. The ELT is a project born from the vision of ESO, or the European Southern Observatory. We must gently pause here to commend ESO. It is truly an amazing organization, a silent powerhouse, and a prolific gatherer of data thanks to its extensive collection of telescopes and instruments. Although it is fundamentally a European project, a collaborative effort across nations, the observatories themselves are strategically based in the serene, arid expanses of the Atacama Desert in Chile. This particular region was chosen with meticulous care due to the inherent elevation of its sites, which means there is significantly less atmosphere, that blurring veil between the telescope and the vastness of space. Moreover, some sections of this profound desert have not witnessed rainfall since records began, ensuring skies of unparalleled clarity, a perfect canvas for astronomical observations. While the individual telescopes of ESO are too numerous to mention them all in our gentle journey, we shall highlight a couple of notable projects, those that stand out as silent beacons of scientific achievement. One such marvel is ALMA, which stands as the premier observatory for gently peering into the cold, dark universe, places like molecular clouds and dusty nurseries where new stars quietly begin to form. It consists of a grand array of 66 antennas, each working in perfect silent tandem, listening to the universe's cool whispers. Another, as we've already softly touched upon, is the VLT, or the Very Large Telescope, which will perhaps unsurprisingly serve as the ELT's direct predecessor, a stepping stone to even greater ambition. The VLT comprises 4 powerful 8.2-meter telescopes and 4 additional smaller 1.8-meter auxiliary telescopes. These can all work either in perfect tandem, like a synchronized cosmic dance, or separately, depending on the precise requirements of the observation. When they work together, they can achieve an exceptionally high angular resolution, or in simpler terms, they possess the quiet ability to discern details 25 times fainter compared to operating separately. These telescopes are currently the flagships of ESO, the brightest jewels in its crown, and they represent the most advanced optical instruments in the world. Silent guardians of our cosmic understanding. Now we gently guide your imagination to these other projects, because to truly appreciate the profound ambition of the ELT, you need to softly compare it to the finest instruments we currently possess. So let us begin with its sheer breathtaking size. Recalling that the VLT, for all its power features 8.2-meter wide mirrors, the ELT's primary mirror is going to be an incredible 39.3 meters across a truly colossal eye gazing into the cosmos. This gives it a light-collecting surface area of an astonishing 978 square meters. A telescope of this unimaginable size means that the main mirror, due to its sheer scale, cannot be a single monolithic piece of glass. Instead, it is going to be segmented a mosaic composed of 798 individual segments, each meticulously crafted and precisely placed. The segmented nature offers a practical advantage. Individual segments can be gently replaced and meticulously cleaned, ensuring the mirror's pristine vision endures. Together, the ELT's main mirror will quietly collect an astounding 100 million times more light than the human eye and approximately 26 times more light than a single VLT unit telescope. It is like gathering the scattered rays of a million distant suns into one focused beam of understanding. Due to the colossal size of this main mirror, several other mirrors are gently necessary to effectively condense all that vast light into the delicate science instruments. This means that there will be a secondary, tertiary, fourth, and fifth mirror in the light path before the light even gracefully reaches the instrument that will analyze it. These smaller mirrors, though secondary, will also be exceptionally special, each a marvel in its own right. The secondary mirror will be the largest convex mirror ever produced, a gently curved surface that reflects light outwards. The fourth mirror in particular will be the largest adaptive mirror ever designed, equipped with a remarkable 8,000 actuators. These tiny, precise actuators, like invisible hands, will allow the mirror's surface to be adjusted with incredibly high time frequencies. It will be adjustable in real time to gently counter the subtle distortions in the image caused by the Earth's restless atmosphere, as well as the minute vibrations caused by the wind gently buffeting the main mirror. This continuous quiet dance of adjustment will ensure unparalleled clarity, allowing the ELT to peer through the atmospheric veil as if it were barely there. Unsurprisingly, with all the immense glass and the profound need for sturdy, unwavering supports, this entire structure, the ELT itself, is going to be extraordinarily heavy. A truly astonishing 3,700 tons of meticulously crafted material, meaning it will require a behemoth of a dome, a colossal protective shell, to support its weight and facilitate its precise rotation. Combine this immense scale with the gentle yet powerful fact that the site is situated in a desert, prone to earthquakes, and these combined specifications elevate the design of the dome to a level almost as ambitious as the telescope itself. Once completed, it will gracefully stand 80 meters high and span 88 meters in diameter. To give you a gentle perspective here, imagine it compared to the ancient Colosseum in Rome or Manchester City's Etihad Stadium. Its scale is truly monumental. To protect the incredibly sensitive mirrors during the harsh daylight hours, these massive doors can gently close, and strategically placed windshields will subtly reduce the amount of wind and fine sand reaching the mirrors. The entire design was meticulously tested in a wind tunnel, ensuring that as much wind as possible is gracefully directed around the structure, allowing the ELT to remain in its tranquil, protected state. While immense effort has been poured into gently reducing the overall weight as much as possible, the total combined weight of the dome and the telescope still comes in at a staggering 6,100 tons. The dome itself is also meticulously protected against the gentle tremors of earthquakes, as it is thoughtfully built on top of massive shock absorbers. These unseen guardians will protect the sensitive equipment from the regular strong earthquakes that Chile, with its dynamic geological nature, frequently experiences. It is a testament to foresight building resilience into the very foundations of this grand cosmic eye. Now, if you have ever gently attempted to photograph the night sky, you will intuitively know that unless you possess an automatic tracker designed to compensate for the Earth's rotation, you're inevitably going to capture some blurry images, especially if you attempt a long exposure. The ELT, in its grand scale, is no different. One of the significant design challenges for the ELT lies not only in its ability to smoothly rotate the entire telescope around its axis, but also to precisely move it up and down all while minimizing vibrations to an almost imperceptible degree. This meticulous control is essential to allow it to achieve the long exposures necessary for capturing the faintest, most intricate details from the cosmos. To achieve this profound stability, the moving part of the dome, that colossal rotating shell, will gently rest on 36 stationary trolleys, each equipped with robust wheels on top. The upper dome, in turn, will feature precisely engineered tracks where these wheels fit securely. These trolleys and wheels have been specially designed to produce the absolute minimum of vibrations possible, ensuring a smooth, almost silent rotation. Next in this intricate dance of precision is the Alt-Az mount, the magnificent machinery that quietly controls the altitude, the up and down movement, and the azimuth, the rotation around the horizon of the telescope. Keeping a colossal 3,700 tons steady and without buckling under its own immense weight means that this mount has to be an impressive feat of engineering indeed. The entire lower pier, that massive foundational column, gracefully rests on 3 circular tracks of hydrostatic ball bearings. These bearings are constructed with such astounding accuracy that their positioning will be correct, aligned to a precision of just a few tenths of a millimeter. Over their full diameter, an almost unfathomable level of precision for such a massive structure. The altitude control section, which delicately holds the mirror itself, will rest on top of the pier, poised to elevate and lower the colossal eye. 2 semicircular plates positioned on either side of this structure will gently rest on top of a cradle of hydrostatic pads. Hydrostatic bearings and pads fundamentally mean that the immense structure is resting on a thick layer of oil, which in turn produces incredibly low friction. This oil layer also serves a dual purpose, acting as a vibration-absorbing cushion, further helping to reduce any subtle vibrations that might be caused by the equipment itself or by the gentle tremors of the earthquakes that Chile regularly experiences. This intricate ballet of massive components floating on oil creates a stability that allows for the clearest possible view of the distant cosmos. The design of this telescope grows even more impressive, even more mind-boggling, when you consider how its creators gently address the persistent distortions caused by Earth's restless atmosphere and the subtle variations brought about by wind and temperature changes. The fundamental problem with ground-based telescopes, a quiet battle they must always wage, is that you have a vast, turbulent ocean of atmosphere above you. This atmospheric veil constantly moves and wobbles the incoming light photons, those tiny messengers from distant stars. This unavoidable atmospheric interference places a hard limit on how much intricate detail you can truly discern in space, like trying to read a finely printed book through shimmering heat haze. Not to mention the mind vibrations that can subtly affect the mirror. Even from the slightest whisper of wind, or the tiny, almost imperceptible expansion or contraction of the massive structure caused by subtle temperature changes. These seemingly minor shifts can cause the segmented mirrors to go out of alignment ever so slightly, like tiny pieces of a grand mosaic shifting out of perfect harmony. As we've gently noted, Engineers have poured immense effort into subtly reducing these problems as much as humanly possible. They have chosen to build the ELT high in the Andes at a breathtaking altitude of 3,000 meters. At this elevation, there is significantly less atmosphere, a thinner veil between the telescope and the vastness of space compared to sea level. Moreover, with the meticulously designed windbreaker, that silent guardian, and powerful ventilation and air conditioning systems, the effects of wind and temperature changes should be kept to an absolute minimum, ensuring a more stable viewing environment. However, even with these heroic measures, this meticulous engineering, it is simply not enough to achieve the profound quality of images that ESO, with its ambitious vision, is quietly hoping for. This persistent challenge, this subtle veil, has not deterred the brightest minds in astronomy and engineering. Instead, it has inspired them. They have come up with a truly ingenious process, a quiet revolution in optics, called adaptive optics. As we gently mentioned, the fourth mirror on the telescope will be a hugely impressive adaptive mirror, a technological marvel in its own right. Imagine its surface constantly shifting and adjusting, like a living, breathing lens. A powerful computer working with astonishing speed will continuously keep track of the turbulence swirling within the atmosphere. It does this by observing the subtle movements of light from carefully selected guide stars, or even from artificial stars that are created by powerful lasers projected high into the atmosphere. These artificial stars are like temporary beacons, allowing the system to precisely map the atmospheric distortions. The computer then swiftly sends precise corrections to the fourth mirror's 8,000 actuators. These actuators, like thousands of tiny invisible hands, will subtly distort the mirror's surface in real time, ensuring that the light reflecting off it hits the fifth mirror almost as if the atmosphere were not even there. If you gaze up at the stars on a clear night and notice that they twinkle, you are witnessing the atmosphere causing the starlight to wobble. This twinkling happens incredibly rapidly, and the distorted mirror of the ELT, with its amazing adaptive optics, has to keep up with those lightning-fast changes in real time, a constant, delicate dance. The powerful computer will also continuously keep track of the primary mirror segments, those 798 individual pieces, to make sure they remain perfectly aligned, ensuring the entire colossal eye maintains its pristine vision. This continuous silent ballet of adjustment, powered by adaptive optics, will mean that images captured by the ELT can be even sharper than those taken by space telescopes, a testament to its much bigger mirror and its ability to actively compensate for atmospheric interference. While adaptive optics doesn't completely eliminate atmospheric distortions, the sheer size of the ELT's mirror means it will easily keep pace with, or even quietly exceed, the James Webb Space Telescope in certain observations, particularly those requiring very fine angular resolution. So where does all this precious light end up after its intricate journey through these precisely crafted mirrors? It flows with quiet purpose into a variety of sophisticated instruments, each meticulously designed to perform a slightly different task, to unveil a specific facet of cosmic truth. Some of the highlights include 3 powerful spectrographs, which gently break down light into its constituent colors, revealing the chemical fingerprints of distant objects. And then there are 2 cameras that will, in their own silent way, put even the impressive cameras on the James Webb Space Telescope to gentle shame, offering an even more profound clarity of vision. Here one can easily visualize the expected spatial resolution difference, a visual testament to progress between the venerable Hubble Space Telescope, the promising James Webb Space Telescope, and the colossal ELT. Each step, a profound leap in clarity. These cameras, these sensitive digital eyes, will work effectively across a broad spectrum, from the visible light spectrum to the mid-infrared. Both cameras will be carefully housed in cryostats, special chambers designed to keep them exquisitely cool. This deep cooling is crucial to ensure that the faint infrared light they are designed to detect isn't suddenly affected by the heat gently radiating off the camera itself. Because James Webb will reside in the cold vacuum of space, it inherently possesses a superior ability to detect the very dimmest of objects, emitting infrared light like galaxies, billions of light years away, whose light has stretched and faded over cosmic time. However, the ELT, with its immense light-gathering power and advanced adaptive optics, will still prove incredibly useful for gently observing nearer objects, especially those shrouded by thick, obscuring dust. Cool dust you see becomes more or less invisible in infrared frequencies of light, meaning the ELT will possess the finest capabilities for seeing through these dusty veils that often obscure celestial wonders within our own galaxy. And what profound science do they hope to quietly collect with these magnificent instruments? The very design and technology of the ELT are impressive enough a testament to human ingenuity. But what it will ultimately see is perhaps the most exciting aspect of all the true heart of its mission. One of its primary missions, a gentle quest, is to use its powerful cameras and spectrographs to examine known exoplanets, those distant worlds with unprecedented closeness. One of its cameras will come equipped with a coronagraph, a clever device designed to block out the overwhelming light from a target star. Imagine a tiny, precise eclipse, allowing the camera to better view the dim, faint light reflecting off the orbiting exoplanets, preventing the brilliant starlight from washing out the delicate image. However, do not expect to see images as crisply detailed as those we possess of the planets in our own solar system. Simply confirming their existence with this enhanced clarity will powerfully validate our exoplanet hunting methods, a quiet triumph in the search for other worlds. Not only that, but its sensitive spectrographs will gently analyze the light emanating from these exoplanets, revealing their atmospheric composition. Scientists will be particularly vigilant, looking out for the subtle clues that these planets might possess the capacity to sustain life. The most obvious substance to look for a clear signal of potential habitability is water, that fundamental elixir of life as we know it. But there are plenty of other markers too. Other chemical whispers, especially if that life were to be similar to ours. These include oxygen, the breath of many living things, methane often associated with biological processes, nitrous oxide and chloromethane, each a potential fingerprint of life's presence. Speaking of planets, the ELT will also turn its powerful gaze towards those within our own solar system. Half the planets in our cosmic neighborhood do not currently have their own dedicated mission, leaving vast swathes of their mysteries unexplored. So the ELT will step in as the next best observatory. We have a tireless sentinel to quietly keep track of them, unraveling their secrets. Scientists will also patiently observe objects normally hidden by dust, like protostars, those nascent stellar embryos and old stars nearing the end of their lives. These observations will provide us with a much better, more complete understanding of how stars gently form and how they evolve over immense periods of time. And speaking of stars, the ELT will also peer past the obscuring dust that often shrouds the most fascinating part of our galaxy, the region directly surrounding the supermassive black hole at the very center of our Milky Way. We currently know of about 40 stars that gracefully orbit this supermassive black hole, a cosmic ballet around an unseen giant. But we expect to be able to detect many more with the increased spatial resolution provided by the ELT, like discovering new dancers in an already known performance. This is a truly intriguing section of space for astronomers, as the supermassive black hole dramatically warps space-time there, bending the very fabric of reality. There is still so much we have yet to understand about such an extreme environment, so many quiet mysteries waiting to be unveiled. The ELT will also gently look towards the centers of nearby galaxies, comparing them to our own, seeking universal patterns in the heart of these cosmic islands. The last profound area the ELT will investigate further, and one that some people might find unsettling to hear, is the enigmatic nature of dark matter and dark energy. Under our current understanding of physics, there is a powerful force still shrouded in mystery that quietly counteracts gravity, relentlessly pushing everything apart. This force is currently known as dark energy. At small distances, the familiar force of gravity overcomes this expansion of the universe, holding things together. But over millions of light years, the universe is expanding rapidly, a gentle, accelerating rush. We've touched upon this cosmic dance of expansion before, and it's a profound mystery in itself. Additionally, galaxies often possess more gravity than they should, based on the visible matter within them, meaning they rotate differently than our theories would predict. This extra unseen gravity is attributed to dark matter, an invisible substance that interacts only weakly with normal matter, yet profoundly shapes the cosmos. To quote ESO itself in its own eloquent words, "What dark matter and dark energy suggests is that our theories of cosmology and particle physics are incomplete or possibly incorrect, and that new physics is out there waiting to be discovered." A key task for the next generation of astrophysical facilities, including the ELT, is to diligently search for, identify, and ultimately characterize this new physics. With its unparalleled ability to better examine the halo surrounding galaxies, which is thought to be permeated by dark matter, and to characterize this elusive substance, the ELT, working in quiet tandem with the James Webb Space Telescope, will observe the universe expand in real time. This has been an elusive goal, something that hasn't been possible to achieve before with such precision. The ELT will provide unique and profound contributions towards deciding whether general relativity, or a subtly modified theory, best describes the expansion of the universe. This includes rigorously testing the behavior of gravity in unexplored regions and meticulously mapping the expansion history of the universe. So the data flowing from this magnificent telescope could, in its quiet way, provide us with a completely new understanding of gravity and the very fabric of physics as a whole. All right, that gently wraps up our discussion here. Sadly, we are going to have to wait a few more years for this colossal project to finish its meticulous construction. But if you are already excited for the James Webb Space Telescope, which will hopefully launch very soon, just wait until this silent giant is finished. With any luck, the James Webb Space Telescope will indeed launch this year. Everything will deploy smoothly, like a perfectly choreographed cosmic dance, and it will soon be sending us fantastic data that we can quietly enjoy in the meantime. Back in April of what was then the year 2022, NASA made a quiet announcement that they would cease operations of an intriguing infrared telescope known as SOFIA. If you have never heard of this particular telescope, you are in for a gentle surprise. SOFIA, an acronym for the Stratospheric Observatory for Infrared Astronomy, is a truly fascinating example of NASA's quiet courage in trying something quite different, something outside the conventional paths of ground-based or space-based observation. And although it did not ultimately prove to be as scientifically productive as they might have initially hoped, the incredible engineering that went into its creation and the unique discoveries it did make firmly established this telescope as an important, albeit unconventional chapter in the rich history of space exploration. But what precisely is SOFIA? It is neither a fixed, unmoving ground-based telescope anchored to the Earth's surface, nor is it a satellite-based one serenely orbiting in the silent vacuum of space. SOFIA is in its most distinctive form a telescope that gracefully protrudes from the side of an airplane. Imagine for a moment a powerful eye peering out from the belly of a massive bird, flying high above the world. As we quietly approach the end of SOFIA's operational journey, it seems fitting to look back on the gentle history of this quirky telescope, to learn about the ingenious design choices that went into its making, and to reflect upon the unique discoveries it quietly made. And finally, perhaps to gently ponder, was it in the grand scheme of things truly worth it? I don't know about you, but when I first glimpsed SOFIA, my mind was immediately abuzz with questions like tiny, eager fireflies. Most depressingly, a gentle query formed, why an airplane? Why not the familiar established paths of a satellite like Hubble or James Webb, or perhaps something firmly anchored to the ground? You might quite reasonably guess that modifying a Boeing 747 to house a telescope would be a more economical choice than launching a colossal satellite into the silent embrace of orbit. And you would be partially right, but perhaps not as completely right as you might initially think. SOFIA, for all its unique approach, was an expensive endeavor both to build and to operate. To draw a few gentle comparisons, consider this: while it cost NASA approximately $1.5 billion to build and successfully launch the iconic Hubble telescope, SOFIA still carried a hefty price tag of $1 billion, a significant investment shared in a quiet 80-20 collaboration with German scientists. That figure, when weighed against Hubble, is not so far off, is it? And the $85 million a year required to simply keep it gracefully flying to maintain its operations is not dramatically less than Hubble's ongoing maintenance costs. In fact, the persistently high cost of SOFIA was explicitly cited by NASA as the primary reason for its eventual discontinuation, a quiet acknowledgement of budgetary realities. You might also gently wonder whether an airplane-based observatory is more fuel efficient than a rocket. Rockets, it is true, are undeniably fuel guzzlers. The mighty SpaceX Falcon 9 rocket, for instance, consumes over 75,000 gallons of propellant, a volatile mixture of liquid oxygen and kerosene, for a single launch. Even with reusable rockets, the fuel top-up alone costs anywhere from $200,000 to $300,000. But SOFIA's Boeing 747, for all its graceful flight, is actually quite comparable in its thirst for fuel. Its capacious tank can hold around 60,000 gallons of a different type of kerosene, and given the fact that it would embark on its quiet scientific flights 3 times a week for 10 hours at a time, burning through about half a tank in one run, all in all that translated to a substantial amount of expensive fuel consumed. Yet despite these considerable costs and fuel consumption, SOFIA possessed some truly unique advantages, some quiet strengths that set it apart. The main profound benefit of space satellites is their ability to ascend above the Earth's atmosphere. Air molecules, like countless tiny lenses, gently refract and distort light, meaning that if you can achieve an altitude above this restless atmospheric veil, you can capture much clearer, crisper images of the cosmos, SOFIA. By flying at altitudes that allowed it to glide above 80 to 90% of the Earth's atmosphere, shared this crucial advantage with a space satellite, it gained a clearer vantage point, a less obscured window to the universe. But unlike a satellite which, once orbiting the planet, remains largely inaccessible, SOFIA, at the gentle conclusion of each scientific flight, could simply come down again. This seemingly simple fact conferred immense practical benefits. It made the telescope significantly easier to maintain, allowing for hands-on adjustments and repairs. And crucially, it made it far simpler to swap out its specialized scientific equipment, like changing lenses on a camera. This flexibility, this quiet adaptability, granted SOFIA a much greater versatility in the kinds of celestial phenomena it could detect and study. This quiet adaptability proved invaluable throughout SOFIA's 8 years of active scientific life, leading to unique insights that we will gently explore later. Still, I don't believe that this practical flexibility was the true underlying reason why SOFIA was conceived as an airplane-based observatory. To understand the real profound motivation, it's important to know a little about the quiet history of flying telescopes. For SOFIA was certainly not the first. It stands as the latest in a venerable lineage of airborne observatories that quietly date back to 1957. That year, the balloon stratoscope was launched, a pioneering effort. The idea was simple: elegantly straightforward affix a telescope to a large balloon, send it soaring 25 kilometers into the sky, and let it quietly take photographs of the sun escaping the lower turbulent layers of the atmosphere. However, the concept of plane-based telescopes wouldn't truly come into its own until the solar eclipse of 1965. Celestial phenomena like solar eclipses are by their very nature deeply tied to specific geographical locations. Depending on where you happen to be in the world, you will experience a better or worse view of a solar eclipse. As the moon gracefully travels between the Earth and the Sun, its shadow sweeps across continents, meaning some regions are treated to the full awe-inspiring eclipse, while others only experience a partial eclipse or none at all. So with quiet ingenuity, NASA decided to mount a telescope on a plane specifically to literally chase the solar eclipse across the globe. This allowed the airborne observatory to remain within the path of totality for an extended period, thus granting it the best possible prolonged view of this magnificent phenomenon. This was a feat that only a telescope on an airplane could achieve. Neither a fixed, unmoving ground-based telescope nor a satellite locked into a rigid orbit could be precisely where it needed to be for such an extended observation. The first such eclipse-chasing telescope was gently placed on a Convair 990 aircraft and was lovingly named Galileo, after the famous astronomer who first turned his telescope to the heavens. Galileo's eclipse-chasing mission proved a resounding success, performing so admirably that NASA, with its characteristic spirit of inquiry, asked itself the age-old question, what if we do a bigger one? This quiet contemplation led in turn to the Kuiper Airborne Observatory in 1974, a larger, more advanced iteration. And then, as a culmination of this pioneering spirit, SOFIA was proposed in 1996 as an even grander, more sophisticated iteration of the flying observatory concept, pushing the boundaries of what was thought possible in airborne astronomy. SOFIA, in its operational form, truly stands as a technological marvel, a testament to human ingenuity in the face of profound challenges. Imagine the complexity of getting a sensitive telescope to work effectively on a constantly moving aircraft. It is about as difficult, metaphorically speaking, as spinning a plate on a stick while attempting to stand on the roof of a moving car. Though please do not try this, SOFIA was designed to capture delicate images of objects millions, even billions of light-years away. To achieve this, it required the astonishing ability to remain perfectly still, utterly stable, even as the colossal plane around it gently rocked with the subtle wobble of atmospheric turbulence, the persistent vibrations of its engines, and the fierce rush of wind ripping into the telescope's open cabin. If the telescope were to vibrate even slightly from any of these dynamic forces, it would be utterly impossible to accurately track the distant stars and planets it was trying to observe. Its vision would be irrevocably blurred. Furthermore, the telescope would repeatedly be supercooled by the frigid temperatures of high altitude, then gently warmed again at ground level, a constant cycle that could potentially lead to subtle cracks and damage to its 8-nanometer precise mirror. A delicate dance with extreme thermal stress. It was an incredible, almost daunting task that NASA and German scientists had set for themselves. Yet they solved these profound problems with quiet ingenuity. SOFIA's telescope is gracefully set on a series of intricate gyroscopes, sensitive devices that maintain orientation, magnetic torque motors which provide precise, subtle adjustments, and high-speed cameras that constantly monitor its position. These combined systems allow the telescope to remain perfectly still, a calm eye in a storm even as the massive plane around it moves. The door that opens on the side of the airplane, revealing the telescope to the sky, comes equipped with an intricately sculpted ramp on one side. This ramp, meticulously tested in wind tunnels, is designed to gently reduce the intense 850 km/h winds, the roaring current, that the Boeing flies at to a mere 80 km/h around the telescope aperture, ensuring a smoother, less turbulent flow of air. And the mirror itself is a masterpiece of material science built using a ceramic glass composite called Zero Dur, which possesses an almost magical property. Virtually no expansion or contraction under vast temperature changes, ensuring its perfect form remains undisturbed. Its equipment is truly unique, almost unparalleled in the world. SOFIA, at its heart, was primarily an infrared telescope designed to perceive the subtle warmth of the cosmos. But thanks to some ingenious additions that were made to its HAWC Plus instrument early on, SOFIA became one of the very few telescopes capable of seeing the polarization of dust clouds. Imagine dust particles, tiny cosmic specks, aligning themselves in response to invisible forces. SOFIA could detect this subtle alignment. This unique capability granted SOFIA the incredible ability to discern magnetic fields across galaxies, like seeing the invisible threads that weave through the cosmic tapestry. However, with its greater size and sophistication compared to its smaller forerunner, Galileo, SOFIA's operational costs began to gently swell, ultimately becoming too great for its scientific contributions to fully justify, leading to its eventual quiet retirement. SOFIA officially began its quiet 5-year mission in 2014 and was subsequently granted a further 3-year extension, a vote of confidence in its unique capabilities. But while in its initial 6 years of operation, the venerable Hubble telescope was cited in more than 900 scientific papers, SOFIA, in contrast, featured in only 178. This disparity led the National Academy's Decadal Survey on Astronomy and Astrophysics in 2020 to conclude with quiet formality that SOFIA did not contribute enough scientific discoveries to justify its consistently high running costs. NASA, with a quiet acceptance of the findings, took their recommendations on board and concluded that there was no longer room for SOFIA in the future landscape of astronomy, especially seeing as there were larger and more exciting infrared telescopes on the horizon that could make more efficient use of the available funding. So was SOFIA merely a quirky idea that perhaps went a little too far, an experiment that ultimately proved too costly for its output? Some in the infrared telescope community, those who understand its unique perspective, would gently argue otherwise. They would point out that its productivity was actually ramping up towards the very end of its life, even as NASA decided to draw its curtains. But ultimately, the true value of its existence, the gentle impact it had on our understanding, can only be weighed by its discoveries, the unique insights it brought back from its airborne voyages. Let us gently examine a few of its most significant revelations, allowing you to quietly decide for yourself. Being an infrared telescope, SOFIA possessed a truly unique advantage. Its gentle gaze was able to see through thick bands of dust that visible light telescopes would struggle to penetrate. Imagine trying to peer through a dense, swirling fog with your naked eye. SOFIA, with its infrared vision, could often pierce that veil. As such, it was able to capture quiet moments like this one in the Orion Nebula. Here, a young star in its vibrant cosmic infancy creates a vast bubble of space around itself by gently blowing the surrounding dust away with its powerful stellar winds, a process known as feedback. It was previously believed that only the cataclysmic events of supernovae, the explosive deaths of massive stars, could achieve such a profound clearing. So SOFIA's quiet discovery that regular stars in their youthful vigor performed the same action has been a key revelation in understanding the intricate process of star formation in the early universe. The stellar winds, like unseen cosmic sculptors, prevent new stars from forming too close to the current one, while simultaneously compressing the dust further out, gently increasing the chances of new stars being created in those more distant, condensed regions. And what about this delicate planetary nebula, NGC 727? By gently analyzing its light signature, its unique chemical fingerprint, scientists were able to make a truly groundbreaking discovery. They found helium hydride in space for the very first time. This molecule, in its simplicity, had long been thought to act as a key building block for more complex chemistry, especially back when the universe was only a tender 100,000 years old in its infancy. But up until SOFIA quietly spotted it here, nestled in the cosmic dust, scientists had had no direct proof that it actually could be found in the vast open expanse of space, having only successfully created it in controlled lab conditions on Earth. This was one of many beautiful examples of theory in its quiet elegance, outpacing direct observation until SOFIA's gentle gaze caught up, Sophia's inherent ability to see in infrared also granted it profound insights into the temperature of the universe. For instance, by quietly noticing that the infrared brightness of a particular debris disk in a double star system, known as DEB, was 10% brighter than it had been a decade prior, scientists were able to deduce a dramatic cosmic event. Two large exoplanets had likely violently collided into each other within the system. This cataclysmic impact would have profoundly heated up the surrounding matter and dust, causing the observed increase in infrared emission. This kind of catastrophic collision, otherwise an incredibly difficult event to detect, was revealed through Sophia's sensitive thermal eye. But my personal favorites among Sophia's many quiet revelations are some of the most mesmerizing images. Those strange, almost ethereal lines that you can see gently weaving through the images of stars. These are magnetic fields, the invisible threads of cosmic force that channel mass in ways scientists had only dimly perceived up until Sophia's unique observations. These fields, like cosmic shepherds, can allow mass to gracefully escape from galaxies, gently guiding it away from the gravitational clutches of black holes, like the one in the center of our Milky Way, thus keeping it peaceful and quiet. Or conversely, they can subtly funnel mass towards black holes, ensuring they are constantly consuming material, growing in their silent power. If you truly wish to understand why the universe works the way it does, understanding the profound role of magnetic attraction is as vital as understanding gravity. And that, in its unique way, is something Sophia gently offered us, like no other telescope before it. From swirling nebulae to distant planets, from the formation of stars to the fundamental building blocks of the universe, Sophia, in its airborne solitude, has quietly peeled back the curtain to reveal fascinating secrets. It has done so in a way that is truly unique, with men and women riding along with it, performing science in real time as it gracefully swept its gaze out across the universe. Perhaps it was a relic of a bygone time, a beautiful experiment, and planes are not the true future of space exploration for the grandest instruments. But without trying new things, without gently pushing the boundaries and innovating, we would never truly know. So what do you think? Was it good that we had Sophia, even if only to quietly say that it didn't achieve as much as we hoped? Or would the money have been better spent elsewhere? What is the true price we can put on experience and knowledge, on the quiet courage to try something different? Either way, for better or worse, for nearly a decade, NASA and German scientists truly did try to stick a telescope out the side of an airplane. And that is a fact that has, for this humble observer, profoundly expanded my understanding of what is truly possible. Now let us softly shift our focus to a remarkable event that, for a brief, thrilling moment, captured headlines around the world, igniting a collective sense of wonder. I'd be surprised if any of you managed to completely avoid the news about the black hole that was imaged at the center of M87, an elliptical galaxy resting roughly 55 million light-years away from us. This colossal behemoth of a black hole is truly one of the biggest that we know of, possessing a suspected mass of around 4 billion suns. This truly makes the supermassive black hole at the center of our own galaxy, Sagittarius A, comparatively puny, a mere dwarf in its shadow, with Sagittarius AU boasting only 4 million solar masses. The M87 black hole, affectionately known as M87K, is not just astonishingly massive, but also truly immense in its physical size. The way we gently measure a black hole is from its event horizon, that mysterious point beyond which not even light, that swiftest of all messengers, can escape the black hole's relentless gravitational pull. To truly give you a sense of this staggering scale, imagine our entire solar system gracefully sitting at the very center of M87K. The orbit of Neptune, that distant icy world, wouldn't even come close to reaching the edge of its event horizon. It even dwarfs the largest known star, Uy-Scuti, which, for all its colossal size, appears like a tiny speck beside the scale of our solar system in comparison to M87K's So a gentle question might arise: why not simply use the venerable Hubble Space Telescope to image M87? After all, it's often considered the best telescope we've had for a long time, isn't it? Well, in some ways, yes, it is unparalleled, but not all telescopes perform the same task or see with the same kind of eye. The Hubble telescope has indeed turned its gaze towards M87, but Hubble can predominantly see only invisible light wavelengths. This particular range of light isn't ideally suited for gently peering through objects like gas and dust, which like thick cosmic clouds block the view. That's why Hubble's breathtaking views of nebulae and galaxies look so incredibly impressive. It excels at seeing all the intricate dust structures and molecular clouds that give these celestial objects their beauty. Black holes, quite unsurprisingly, do not produce any light themselves, which makes them exceedingly difficult candidates to directly observe. What we can see, however, is the incredibly bright material found swirling in a black hole's accretion disk, a vibrant, tumultuous whirlpool of gas and dust spiraling inwards. Still due to the vast amount of material in a black hole's accretion disk actually observing the black hole itself, its dark silhouette is very challenging in the visible light spectrum. Imagine trying to see a tiny shadow within a blindingly bright halo. A visual representation, a gentle journey through different wavelengths of light, beautifully illustrates what the accretion disk of a black hole would look like. Starting with shorter wavelengths, as the wavelength decreases, the material surrounding the black hole becomes progressively more visible, more defined. So the quiet secret to imaging a black hole to revealing its dark form is to precisely select the frequency of light, to get it just right to provide a delicate balance of what's visible in the surrounding chaos. And that, dear listener, is precisely what the Event Horizon Telescope, EHT, is. It is not a single monolithic eye, but rather a colossal array of ground-based radio telescopes scattered throughout the world, each working in silent, perfect unison to gently image black holes like M87T. An array, by combining the signals from geographically separated telescopes, effectively creates a much bigger aperture, an imaginary dish as vast as the Earth itself. By synchronizing these telescopes together from all corners of the planet, it allows for the creation of a much sharper, more detailed image than any single telescope could achieve on its own. Although it should be gently noted that this does not in fact make the whole Earth a giant mirror. The light collecting capabilities are only as large as the collective size of the mirrors used. It is merely the aperture, the resolution, that profoundly improves, allowing for an incredibly keen eye. The other major difference between the Event Horizon Telescope and Hubble is the astonishing angular resolution it can achieve. Even though M87.6 is an unimaginably massive black hole, the distance to it is so vast that the Event Horizon Telescope is effectively trying to discern the equivalent of a grapefruit resting gently on the surface of the moon. An object that from our perspective spans only 30 microarc seconds across. Hubble, for all its power, does not even come remotely close to this breathtaking resolution. In reality, when humbly studying astronomical objects, it is profoundly important to utilize all the frequencies of light, each a different lens, as this provides a much more complete, nuanced picture of the object in question. For instance, while the Event Horizon Telescope can peer closely at the black hole itself, other telescopes can gracefully observe the accretion disk, the powerful jet of particles blasting away from the black hole, and the entire galaxy itself, each offering a unique piece of the cosmic puzzle. I think this gentle contemplation leaves but one final question about imaging black holes. Why did they choose to image M87 Kurzmo and not the black hole found at the center of our own galaxy, Sagittarius A? Although our galactic black hole is smaller, it is by cosmic standards much closer to us, so it must be easier to image, right? Well, the subtle difference lies in their activity. M87E is significantly more active than our own quiet black hole. This heightened activity, combined with its immense size, makes it a much easier target to observe. It is thought that roughly one solar mass, a colossal amount of material, is gently falling into M87T's black hole from its accretion disk every 10 years, and the powerful jet of particles blasting away from this black hole, stretching for tens of thousands of light years, stands as a silent testament to this tumultuous activity. On the other hand, Sagittarius A is remarkably quiet, almost serene, meaning it is a lot harder to discern at the moment. But the Event Horizon Telescope will be turning its powerful gaze towards our own galactic center soon, so it won't be long before we can gently compare the two, revealing more of their silent secrets. Now let's gently transition our thoughts to another profound mystery, one that truly captivates the imagination: rogue planets. These are, in essence, planetary-sized objects that are not gravitationally bound to a star. Imagine a planet adrift in the vast cosmic ocean with no sun to warm it, no star to guide its lonely journey. We don't yet fully understand how these solitary wanderers formed. Perhaps they quietly coalesced within a planetary system, just like our own, but were then violently ejected during the system's turbulent, chaotic beginnings, cast away to forever roam the galaxy alone. Following that quiet thought, perhaps our own solar system in its early formative years also harbored additional planets before they were, by some cosmic twist of fate, cast away into the silent, starless void. Rogue planets could also be protostars, nascent stars that simply failed to accumulate enough mass to ignite their nuclear furnaces and become true luminous stars. Or they might even be brown dwarfs, those intriguing failed stars that are too massive to be planets, but too small to be stars. We expect there to be billions, perhaps even trillions of these solitary wanderers out there in just our galaxy alone, a silent multitude. However, because they are so incredibly hard to detect, this truly remains an educated guess at best, a whisper of a possibility. Yet since the turn of the century, we have quietly begun to detect a few of these mysterious objects. How can that be? We might softly ask, when there are no stars to light them up, no internal glow to betray their presence. If they are utterly pitch black, how do we have any hope of detecting them at all? Well, this is where a truly fascinating detection technique, both ingenious and subtle, gently comes into play. It is called gravitational microlensing. On this channel, we have gently explored various exoplanet hunting techniques. In the past, each a different method for discerning the unseen. Primarily, we've discussed the radial velocity method and the transit method. The radial velocity method, like a sensitive cosmic ear, measures the subtle wobble of a star, a tiny gravitational tug caused by the unseen presence of orbiting exoplanets. Imagine a distant bell vibrating ever so slightly as unseen forces influence it. The transit method, on the other hand, measures the brightness of a star over a long period of time, patiently looking for tiny, almost imperceptible dips in the star's brilliance when an exoplanet gracefully passes directly in front of it, casting a momentary shadow. However, these familiar methods are primarily useful for detecting exoplanets that are bound to stars, and generally the planets they tend to reveal are quite large, often gas giants, and orbit very close to their host stars. The gravitational microlensing method, however, is a truly exciting and subtle approach because it can not only find exoplanets that are much further away from their host stars, but it also possesses the astonishing ability to detect planets as small as Mars, or possibly even smaller than that, and still discern their presence. Additionally, and this is where it becomes truly profound, rogue planets, those solitary wanderers with no star at all, can be detected with this ingenious method. It sounds almost too good to be true, doesn't it? A way to find invisible worlds. But as with many elegant solutions, there is one gentle catch. So how does this remarkable technique truly work? Gravitational lensing is a well-known phenomenon in astronomy, a beautiful consequence of Einstein's theory of general relativity, and it has been utilized for years to detect some of the most distant and ancient galaxies that we know of. Einstein himself predicted this phenomenon back in 1936, a quiet whisper of a grand truth. And with the steady development of telescope technology, it has been beautifully confirmed by countless observations, a testament to the universe's elegant design. Basically, the further away a light source is from us, the dimmer it becomes, its light gently scattering into the vastness. This fading is a direct result of the inverse square law, which tells us that light photons spread out as they travel, meaning the further away you are from the object, the fewer photons that reach your eyes. However, when there is a celestial body with a truly large amount of mass, like a colossal galaxy or a vast cluster of galaxies, the immense mass of that object actually warps the curvature of space-time around it. Imagine, if you will, a heavy ball resting on a stretched rubber sheet, creating a dip. Light, those intrepid travelers, follows this curvature of space-time. This means that if light emitted by a distant object travels past a massive foreground object, the light photons that would have otherwise continued on their straight path actually bend around, guided by the foreground object's gravity. This subtle bending causes the background object to appear brighter to an observer here on Earth than it otherwise would have done, simply because more light photons are gently guided towards us. Gravitational lensing becomes very obvious, quite dramatic even when we quietly observe the biggest types of cosmic objects, like galaxy clusters, because these immense structures warp space-time the most profoundly. This means that if we happen to be aligned just right with a galaxy cluster, positioned between us and a truly distant galaxy, the distant galaxy will appear much brighter, its light amplified and focused towards us. The light from the distant galaxy bending around the nearer galaxy would also actually make the distant galaxy appear stretched, sometimes even taking on the ethereal form of a perfect ring, a cosmic halo. You may have seen these breathtaking Hubble images before, where distant galaxies appear totally distorted, almost smeared across the sky, thanks to this powerful gravitational lensing effect. And for a clearer understanding, imagine a simple CGI example that shows this phenomenon, helping us grasp why this subtle bending of light occurs. Now, as we gently noted more recently, the ingenious use of gravitational lensing has also been extended to help astronomers detect the elusive presence of exoplanets. While stars and planets are infinitely less massive than colossal galaxy clusters, the subtle bending of light, gravitational lensing, still occurs to a small yet detectable degree. When a foreground star gracefully transits in front of a distant background star, the distant star will briefly become brighter, its light subtly amplified as it follows the gentle curvature in space-time around the foreground star. Additionally, should this foreground star possess an exoplanet or multiple exoplanets, the distant background star will also exhibit tiny subtle increases in brightness when these planets in turn transit in front of it. This intricate process, this delicate detection, is precisely what we refer to as gravitational microlensing. This process is so remarkably accurate, so exquisitely sensitive that small exoplanets, even those the size of Earth or Mars, can be detected, and potentially even large exomoons orbiting these distant worlds might be revealed. Astronomers simply need to meticulously measure the tiny fleeting peaks in brightness to gently distinguish between the individual bodies orbiting the foreground star, like deciphering a secret code hidden in light. Now, as we hinted earlier, there is a gentle catch with this method, a subtle limitation, and that is that star transits where one star passes directly in front of another from our perspective are actually quite rare. This is because they truly need to be aligned just right from our vantage point, and the galaxy itself is simply enormous. There is so much empty space between stars, vast cosmic voids. This inherent rarity is why, up until now, the transit method where planets cross in front of their own stars has had a far better success rate at detecting exoplanets. This is because exoplanets orbit and transit their stars much more frequently than stars transit other stars. So, in order to spot these fleeting microlensing events, What we quietly need is the ability to observe a truly huge swath of the sky in one go, a wide, patient gaze. Enter the Nancy Grace Roman Space Telescope, previously known in its conceptual phase as the Webb Observatory. This telescope, gently poised to be launched in 2025, is comparable in size to Hubble and promises to provide images with a sharpness similar to the iconic Hubble Space Telescope. However, its true power lies in its breadth of vision. The Roman Space Telescope will be equipped with a colossal 288-megapixel camera and an astonishing 0.28 square degree field of view, which is 100 times larger than Hubble's field of view. With this expansive vision, it will be able to continuously keep track of a much larger section of the sky, tirelessly monitoring for those elusive microlensing events. How does all of this fit in with our quest for rogue planets? Well, much like stars, rogue planets that happen to gracefully transit in front of a distant background, star will also cause that star to become slightly brighter, a subtle flicker in the cosmic background. And if the Roman Space Telescope is patiently looking at that particular section of the sky, it should, in theory, be able to detect it. In fact, throughout its initial 5-year mission, scientists quietly hope that the Roman Space Telescope can provide us with a much better indication of how many rogue planets and Earth-sized exoplanets are truly out there, gently mapping this hidden population. Now, while it is certainly possible that rogue planets could be found in any section of the sky, drifting through the cosmic void, the Roman Space Telescope will wisely focus its time looking towards the crowded center of our galaxy. There are quite simply a lot more stars clustered together in that region, meaning that stellar transits, and thus microlensing events, should be more frequent. This strategic focus will greatly increase the chances of spotting these subtle microlensing events, allowing us to find those otherwise invisible wanderers. It is truly amazing to me that there are such ingenious ways to detect these otherwise unseen objects, these invisible worlds that emit no light. All you need to do is patiently observe the subtle brightness of a background star, and as a rogue planet passes in front of it, the tiny gravitational microlensing event will quietly reveal key details about the rogue planet, such as its elusive mass. So, have we detected any rogue planets using this method at all? As it happens, yes, we have. There are a few ground-based programs tireless in their quiet hunt for rogue planets currently operating around the world, such as OGOL and MOA and Super Mako. At present, these dedicated efforts have collectively found 22 rogue planet candidates in all. The most exciting one, a true whisper of discovery, is OGIL 2012 BLG 123. If this rogue planet is gently confirmed, it will be by some margin the smallest rogue planet ever discovered, being roughly the mass of Earth. How a body like this comes to be free-floating in the vastness of space, unbound by a star, we don't really know yet. We are still in the very early stages of discovery in this fascinating field, but as the James Webb Space Telescope and the Roman Space Telescope launch and begin their quiet work, hopefully we will uncover much more information about these intriguing solitary objects, adding new chapters to their silent stories. So there you have it, a glimpse into how we can detect the invisible objects that are rogue planets, those silent wanderers of the cosmos. Now, if I were to ask you to gently close your eyes for a moment and imagine a telescope, what would you see? Perhaps you might picture an old wooden cylinder, lovingly crafted with lenses at both ends, much like the one that Galileo Galilei first used to gaze up at the heavens and discern the dancing moons of Jupiter. Or perhaps your mind is constructing a grand cathedral-sized dome, rising majestically against the night sky, housing mirrors as vast as tennis courts, like the formidable telescopes nestled high up in the mountains of Chile and Hawaii. Or your thoughts might even drift to visions of enormous dish-like structures, silently pointing towards the cosmos, reminiscent of the infamous Arecibo telescope that once quietly captured radio waves from across the vast cosmos. What you are probably not imagining, however, is a cubic kilometer of ancient ice hidden deep beneath the frigid surface of our planet's south pole. And yet, deep below the incredibly cold, silent landscape of Antarctica, there lies precisely this, a truly extraordinary telescope, resting within one of the most inhospitable environments on Earth. This unique observatory is designed not to observe visible light or radio waves, but instead to seek out one of the most unusual and elusive particles in the entire universe. Join us now as we gently journey to the IceCube Neutrino Observatory and participate in its quiet hunt for neutrinos, those mysterious entities also affectionately known as ghost particles. If you stood upon that vast icy surface, that quiet, desolate expanse, you might not be subtly aware that some of the rarest and most profound events in the universe are being observed day and night, deep beneath your very feet. Located at the most southerly human-occupied base in the world, the Amundsen-Scott South Pole Station IceCube quietly makes use of the very ice in which it is meticulously built to observe high-energy neutrino particles. But why, we might gently ask, this extreme environment, this bizarre and unconventional design? The answer, like a cosmic riddle, is because neutrinos are weird. Truly, profoundly weird. Neutrinos are fundamental particles, much like the quarks that make up protons and neutrons, or the electrons that orbit atomic nuclei. Most of these elusive neutrinos that arrive at Earth embark on their journey from our own sun, where they are gently released from the nuclear fusion reactions, raging intensely inside its fiery core. Other neutrinos will have originated from far more cataclysmic and dramatic cosmic events, such as the violent aftermath of a supermassive black hole's activity, the spectacular explosion of a supernova, or any other cosmic event possessing enough raw energy to tear atoms apart into their most basic subatomic particles. Similar to electrons, neutrinos belong to the lepton family of particles. This means that they do not interact with other matter through the strong nuclear force, that powerful glue that binds other subatomic particles, like protons and neutrons, together within an atom's nucleus. And unlike electrons, neutrinos are electrically neutral, carrying no charge, and possess almost no mass whatsoever. This remarkable combination, their lack of charge and their almost infinitesimal mass, means that they can only interact with other particles through the weak nuclear force, one of the four fundamental forces of nature. This delicate, almost imperceptible interaction is precisely what grants them their ghostly quality, making them one of the most difficult particles for scientists to detect. They are so elusive, so shy, that even when we do manage to gently measure their presence, it is only through the subtle impact they have on other particles, like watching the ripples from an unseen stone. If that wasn't spooky enough, consider this: neutrinos can quite astonishingly pass through our entire planet, through its crust, its churning mantle, its fiery core, and every other layer, without acknowledging the existence of a single atom. They simply fly straight out of the other side, completely unnoticed, as if our planet were not even there. Trillions upon trillions of neutrinos are surging through your body, through every cell, every single second, right now. And yet, over your entire lifetime, there is only a tiny, almost negligible 1 in 4 chance that even one of those countless neutrinos will interact with an atom that belongs to your body. Here, we find further profound demonstration of the neutrino's complete refusal to engage with matter in the universe. To grasp their elusive nature more fully, imagine photons, those familiar particles of light created in the same nuclear reactions deep within the sun. These photons may take a staggering 1 million years between bursting out of the sun's scorching center and finally leaping off its surface into the vastness of space. They are constantly absorbed and re-emitted, caught in a cosmic pinball game, bouncing in random directions over and over again by the dense atoms within our star. This results in an incredibly long meandering path to finally escape. Neutrinos instead zoom straight out of the sun in a mere 2 seconds, traveling at almost the very speed of light itself. As far as the standard model particles go, Neutrinos are certainly the more coy and antisocial of the group, preferring their solitary, unimpeded journey. But on rare and momentous occasions, these shy neutrinos do indeed mingle with other matter. And in that brief, subtle interaction, they can create a dramatic cascade of energetic particle events, rippling outwards in their wake. It is precisely this cascade, these tiny fleeting echoes, that IceCube is tirelessly trying to observe. They might seem strange, but the 5-160 detectors, affectionately known as DOMs, digital optical modules, suspended deep down between 1.5 and 2.5 kilometers in the profound darkness of the ice shelf, are in fact light detectors. The sun's rays, of course, have been completely swallowed up by the thousands of meters of compressed ancient ice that lie above. But that doesn't mean there is no light at all down here. When high-energy neutrinos and cosmic rays, those energetic visitors from beyond, gently penetrate into the incredibly clear and dense ice and finally collide with the atoms of frozen water, they cause other particles, such as muons, to spring into existence. These muons are the key, the quiet signal to identifying a neutrino interaction. As the newly created muon hurtles through the incredibly clear and dense ice, it can quite astonishingly exceed the speed it takes light to move through that same ice. Now let's be absolutely clear, nothing can move faster than light in a perfect vacuum. That is a fundamental law. But in other materials, such as ice or liquid water, or even glass, light slows down. This phenomenon is not a violation of the laws of physics, but rather a fascinating consequence of light slowing down more than other particles as it propagates through these denser mediums. As the muon silently races beyond its photon counterparts, it generates a shockwave of blue light expanding outwards in a precise, cone-shaped pattern from its path. This eerie, beautiful phenomenon is known as Cherenkov radiation. Cherenkov radiation is most commonly associated with nuclear reactors, where it eerily glows through the water that surrounds their cores. This captivating blue hue, seen in nuclear cores, and strangely also deep down in the pristine ice of the South Pole, can look peaceful and atmospheric, almost ethereal. But it is in fact the quantum equivalent of the sonic boom that roars out from a supersonic jet plane flying overhead. In the case of the jet plane, it moves through the air, and pressure or sound waves are pushed out in all directions. As the jet's speed builds up towards the speed of sound, the waves directly in front of it start to bunch up, forming a shock front of high pressure. When the plane finally exceeds the speed of sound, it smashes through this shock front, causing a rapid dramatic change of air pressure. This is the sonic boom. The shock front then travels out in a cone, silently trailing behind the aircraft, which observers on the ground will hear as a thunderous cloud. In the case of the muon within the ice, the particle is not pushing air, but instead subtly disturbing the electric fields of the water atoms in the ice with its electromagnetic charge. This disturbance gently polarizes the water molecules, causing their charges to temporarily align. As these molecules depolarize back to their usual uncharged state, they release the energy that forced them into polarization as photons of blue light radiating outwards in all directions. This intricate dance of polarization and depolarization. This creation of blue light is happening continuously all along the path the muon takes through the incredibly clear ice. If the muon were traveling slower than light in the ice, there would be no distinct wavefront, and all the expanding light spheres would destructively interfere with each other, gently canceling out to complete darkness. But since the muon is traveling faster than light in the ice, this shock front of constructive waves in the beautiful form of blue light is created. The thousands of digital optical modules DOMs that comprise IceCube are meticulously primed, incredibly sensitive to detect this signature blue light, flashing faintly through the vast, dark expanse of the ice. The minuscule differences in time between when one DOM registers this faint flash and when its neighboring DOMs detect it allows scientists to incredibly accurately triangulate the precise path of the muon, and by extension, the exceptionally energetic neutrino that created it. This allows them to trace its journey back through the ice and ultimately, back through the universe, all the way to its elusive cosmic origin. These orb-like detectors, each a silent sentinel, are marvelous, intricate devices designed to detect the very faintest luminous hints in the massive icy expanse. Each dome is carefully encased in a 13-inch spherical glass pressure case, which meticulously protects the delicate electronics inside from the extreme cold and immense pressure of the Antarctic ice. Inside, there resides a photomultiplier tube, a device sensitive enough to detect even a single photon, that most ephemeral of particles, along with various other components that amplify the signal and convert it into digital data. This precious data is then silently transmitted up the cables to the surface, ready for human eyes to gently scrutinize. With so many detectors making up this grand three-dimensional array, there is quite naturally a vast amount of data to process. A whole terabyte of measurements are quietly captured every single day, and hundreds of gigabytes of that precious data are then beamed by satellite to scientists across the planet for them to meticulously comb through, sifting for the faintest presence of their ghostly quantum target. Within this immense trove of data lie the subtle imprints of many particles arriving from beyond our atmosphere. The vast majority, however, are cosmic rays. IceCube detects around 275 million of them daily, a constant bombardment. Cosmic rays are fascinating in their own right, truly energetic particles. But for those seeking the even rarer neutrino interactions, they serve as an obscuring curtain of noise. Neutrino interactions occur 1,000,000 times less frequently, with only around 275 detected daily. But even with the roughly 100,000 neutrino detections that IceCube makes each year, almost all of them are generated within our own atmosphere as subtle debris from collisions of cosmic rays with atoms in the gas that surrounds our planet. They are not from cosmic origins themselves. The key word here, the quiet distinction, is almost. On the 22nd of September 2017, an exceptionally bright burst of Cherenkov radiation was registered by IceCube's array of detectors. Working together, the DOMs used the tiny, almost imperceptible time differences between when they each detected the flash to precisely trace the path of the muon, and by extension, the exceptionally energetic neutrino that created it. They traced it all the way back to a powerful and mysterious cosmic source lurking out in the profound depths of our universe, a blazar. A blazar, in essence, is a supermassive black hole at the center of a distant galaxy, but one that is actively hurling powerful jets of particles directly towards Earth. This particular discovery was monumental. It was not the first time that IceCube had detected neutrinos from deep space, those ancient distant whispers. But this detection was the very first to trigger a real-time alert to telescopes across the globe, quietly indicating that there was something profoundly significant to look at in that specific direction. IceCube and neutrinos had, in that moment, truly entered the world of multi-messenger astronomy. In this exciting new realm, the cosmos is studied not just through light, as it has been for most of the history of astronomy, but also through gravitational waves, cosmic rays, and now significantly neutrinos. Neutrinos, those elusive ghost particles, offer a particularly useful window for us to peer through, because like gravitational waves, they can arrive at us before the light from a major astronomical event. This is due to their ghostly nature that we talked about earlier. Neutrinos take a very direct, unimpeded path to our detector, whereas light, those more social photons, faces many obstacles like dust clouds and tangled magnetic fields that interfere with its journey and subtly slow it down, forcing it to wander. IceCube is now fully integrated into a planetary network of observatories, a silent global sentinel constantly scouring the skies for signs of high-energy cosmic events. It stands ever ready to quietly inform radio dishes, mirrors, and lenses precisely where to point, guiding them to catch sight of rare and transient phenomena that we would otherwise miss completely. IceCube is the noble watchman, sounding the alarm to rally an army of telescopic troops across the globe, gently commanding them where to aim to catch sight of raging cosmic fires. Even further to that, IceCube can give us a truly unique view into the very heart of these phenomena, because unlike photons, neutrinos can escape relatively unscathed from incredibly high-energy environments. Imagine the core collapse of supernova explosions, those cosmic fireballs, or the cataclysmic merges of unfathomably dense neutron stars, or even the searing fury of supermassive black holes. Neutrinos, in their ghost-like essence, can deliver new and different information that light-based telescopes are simply blind to. So to speak, the neutrinos it detects can hugely broaden our understanding of all these events and of the most fundamental nature of the universe. During these extreme events, physics is pushed to its absolute limits. Particles are accelerated to speeds and energies thousands of times greater than what we can achieve in our most powerful particle accelerators on Earth, like those at CERN. This allows physicists to rigorously test their theories and use the quiet arrival of neutrinos at IceCube to make profound new discoveries, not only about the behavior and properties of neutrinos themselves, but also about the elusive nature of dark matter, and even about the very ice in which it is built, revealing its hidden properties. This is why so much immense effort was poured into building such an extreme and unique telescope as the IceCube Neutrino Observatory. It was an effort that took 7 years to meticulously complete, with work pausing during the harsh Antarctic winter when planes are shut out from Earth's most southerly continent by the brutal, unforgiving weather. Construction could only briefly resume for the precious summer months, from November to February. Over those 7 dedicated years, the IceCube team drilled 86 colossal holes, each 2.5 kilometers deep, using 18,000 liters of fuel per hole, and melting an astonishing 750,000 liters of ice in the process. All of this immense undertaking was so that a few hundred dedicated scientists could live and work in one of the most inhospitable environments on our planet, all in an attempt to understand the most extreme events in our universe, and to capture a fleeting glimpse of the most elusive particle in the universe. Neutrinos are truly the phantoms of the particle kingdom. It takes bold and ingenious ideas from ambitious scientists, a profound commitment to pushing the boundaries of what is known to witness even a single neutrino. We know so little about them compared to other particles, those more sociable entities, but they are just as important in furthering our understanding of the fundamental laws of nature. With each neutrino detected, each subtle whisper from the cosmos, we are moving closer to comprehending the universe and the powerful forces that have shaped it.